welcome everyone. Welcome to our third Nix Lecture. My name is Alberto Saleo. I'm the chair of the Department of Material Science and Engineering. And well, you are a collection of alums, students, friends of the department, and it's great to have you all here. Like every year, it's now become a habit. I want to acknowledge two of our alums in particular. Well, first of all, I want to acknowledge Bill, who's here with his daughter Cynthia. Thank you, Bill. And we have Wally Rines, who comes every year. Thank you, Wally. And Mr. Nakagawa, who came all the way from Japan, the CEO of Nakagawa Steel. So thank you for coming. I just wanted to spend a couple of minutes just reminding you where this event comes from. We had a centennial in 2019. And we all decided that we'd like to see each other more often than once every 100 years, and everyone enjoyed being here together. And this is a slide that I showed you at the centennial. This was the state of our department in 2019. We had 17 faculty. This is a slide made with data that Bill Nix gave me in a spreadsheet. We had 17 faculty, 16 undergrads, 136 PhD students, 55 masters, and 65 postdocs. And I was actually exactly the average age of our department at the time. It's interesting, if you take a slope of 1, you know what it means. If your average age increases by 1 every year, you know what it means. And it turns out in 2019, this is, arguably plus or minus, this is sort of how we were. And the question was, what's going to happen next? And I'm happy to report that what happened next is the average age went down. So that's great. What's sad is that I wasn't able to pull that trick. And so unfortunately now I am at the highest, the higher end of the average age. But what this means is that we've been able to hire some great new faculty in materials theory, semiconducting materials, 2D materials, sustainable manufacturing and X-ray imaging, TEM, and also advanced data analysis. So this really has been a great run for our department. We've hired some great new faculty, and we're off to a really fantastic future. I also want to put an emphasis on something else, which is we've also hired 2 lecturers, and that's really done wonders for our undergraduate program. Hao Shui and Enzi have joined our department just recently, and it's been great also to see how our students feel like they're part of our community a lot more because our lecturers do a great job. And so this is where we are now in 2025. So you have 23 faculty. The number of undergrads has doubled, which I think is pretty spectacular. The number of PhD students has increased by 40%, and our postdocs have increased by about 20%. Master stays the same because we cap it at about 55 because that's how many we think we can handle for our classes. Our masters is all in person. So it's really been a great 5 years for our department, and you'll hear a lot of great research. Today you heard every Nix lecture, we give research presentations from our young faculty showing what they're about to do, what they've been doing, and where the department is going. Today I wanted to emphasize something slightly different, which is the teaching. Thanks to our lecturers, we have also new classes that attract our students. So Hao Shui has been teaching a class on the science of texture and food, edible materials. And what's interesting here is that you always hear about sort of the chemistry of cooking, but there's a whole aspect of texture, of, taste is also texture. And Hao Shui focuses on that, and that's a very much more materials-y type of topic. And she actually teaches a lot of the fundamental materials concepts like diffusion, phase equilibrium, and so on, but in a different context, and students actually end up eating what they prepare in the lab. They actually work in a kitchen. And this has been a huge success. It will also be advertised on the Stanford website relatively soon, I believe. Enzi, on the hand, has a focus on a different type of class. In addition to sort of disciplinary depth, communication, science communication is really important. Enzi put together a class on visual communication in material science. This pairs very well with our labs where students have to write reports, and this teaches them how to present their data in a very understandable manner, and you can see their animations of face space. Also, there's a lot of sketching, so they sketch things from other classes, and they learn how to sketch things that communicate their concepts as efficiently as possible. And essentially, they go through a project where it goes from sketching a figure to actually building it in a way that it communicates what they want to communicate as effectively as possible. So I'm personally really excited about what our lecturers are doing for our students. Of course, our research has always been strong, is only always getting stronger, but I wanted to expose you to a different aspect of the department that I think is really new and exciting. So with that, without further ado, I think we should move to the rest of our program. And I'd like to introduce you to Sarah Heilshorn, our Associate Chair, who will do the introduction and the moderation for our faculty speakers. So again, thanks everyone. Oh, one last thing, sorry. Actually, two last things. So one of them is our students are really excited to meet alums. And at the poster session, there will be actually a poster from our Materials Research Society students. So stop by, chat with them, connect with them. They really want to know what happens when you have a degree in material science, what are the different career paths, and they want to get to know you and connect with you. And then the other thing is I wanted to thank our staff for organizing this event. Lisa Ewan in the back, our department manager, and all her staff for organizing an event that behind the scenes is a lot of work, and then once you're here, it always works really smoothly. So thank you, Lisa. So with that, Sarah, the floor is yours.
Thank you, Alberto. I'm so pleased to welcome you all here today and to kick us off on the scientific portion of our program. You're in for a real treat. We have two fabulous junior faculty members who will be sharing with you a bit about their work, and we'll have time for questions and answers afterwards. So as you're listening and being inspired, think about what questions you have for both of them. So the first speaker this morning is going to be Professor Guosong Hong. Guosong started his PhD career here at Stanford in the Department of Chemistry before moving on to Harvard for a postdoctoral fellowship. He returned to the campus and joined the Materials Science and Engineering Department in 2018, and he's also one of the core faculty members of the Wu Tsai Neurosciences Institute. So this represents a partnership between a research institute on campus devoted to neuroscience and the academic home being the Materials Science and Engineering Department. And Guosong's research really bridges these two disciplines in incredibly creative ways. For this innovative work, he's been recognized with the National Science Foundation Career Award and also the National Institutes of Health Pathway to Independence Award. Keeping on the theme of our department is really valuing teaching, Guosong is also the winner of the Walter J. Gores Award for Excellence in Teaching, which is the highest honor that a faculty member can receive for teaching. So you're in for a good treat. Guosong.
Thank you so much, Sarah, for a very nice introduction. It is such a distinct honor and pleasure to speak at the Nix Lecture. I actually fondly remember when I started 6 years ago, I had the privilege of having lunch with Bill. And when I was asking him for the advice he would give to a junior faculty, and then I still remember, he told me, go to the fundamentals. So today, I would like to share a story with you that I would like to use this story to honor his advice that demonstrates how the fundamental principles in material science can potentially transform biological research by making the living biological tissue transparent using ingredients actually found in this bag of Doritos. So the animal kingdom features many species with very unique and intriguing optical properties in their tissues. For example, the glass frog has transparent skin and muscle, enabling us to see through their body to visualize internal organs. Chameleons, on the other hand, can change the color of their skin in a way to adapt to their environment. However, in contrast, most mammals, including humans, cannot change the transparency of the skin or any part of the body so easily. So this raises an interesting question. Why would the transparent tissue be beneficial to us at all? The motivation behind transparent tissue arises from the need to deliver light deep into the tissue and the image deep into the tissue in a wide variety of applications in biology and medicine, ranging from optogenetics, the light-controlled gene editing, endoscopic imaging, all the way to photodynamic and photothermal therapy. However, we know that our body is actually not transparent to the visible light, which you can confirm by looking at your hand. You can barely see beneath the very surface of the skin in the hand. And this actually imposes a significant challenge for all these technologies using light in biology and medicine, often necessitating invasive approaches to remove overlying tissues to enable deep tissue light delivery and imaging. So we wanted to ask a question. Why is the biological tissue intrinsically opaque? So in a close collaboration with Mark Brungersma in our department, and also working alongside a team of very talented graduate students and postdocs, Zihao, Yishu, Nick, and Carl, we actually took a deeper look at how light interacts with the tissue. We found that when light penetrates the skin, it undergoes multiple scattering and absorption processes, both of which lead to the attenuation of light intensity. Compared to absorption, scattering actually contributes to 10 times more attenuation of the light across the visible spectrum in most of the tissues, as you can see from the bottom graphs. Therefore, the key to change the transparency or achieve transparency in biological tissue lies in the reduction of scattering, much more so than reducing absorption. This begs the question, what causes scattering in the tissue? Biophysicists have studied this extensively in the past decades, and they have realized that it is the refractive index mismatch at a microscopic scale that leads to this scattering process. We know our body is a giant bag of water, with most of the soft tissue comprised of 70% of the soft tissue comprised of water with a low refractive index of 1.33. This contrasts very significantly with non-aqueous components in our body, such as lipids and proteins. They have a high refractive index in the range of 1.4 to 1.5, and they're dispersed in water. This is quite similar to milk. If you take a microscopic image of milk, you realize there are actually many liquid droplets, as you can see from the bottom right graph. These have a high refractive index dispersed in the aqueous water environment. And it is this same refractive index mismatch at the microscopic scale that leads to the scattering and opacity of both milk and also the biological tissue in our body. Having recognized this as the origin of scattering and the reason for intransparency or opacity, people have developed a wide range of methods, these are usually called tissue clearing methods, to improve the transparency of the tissue. There are basically two categories of such technology. The first one is called dehydration, basically replacing low-index water with high-index organic solvents. And the other way is actually the other way around, which is replacing the high-index lipids, removing the high-index lipids, and replacing them with water. This is called hyperhydration or hydrogel-based method. As you can see, since both methods involve the removal of either water or lipids, and since both water and lipids are essential for sustaining life, these approaches are not applicable in live animals. So the key to achieve optical transparency in live animals is actually deeply rooted in the fundamental principles in material science, as we realized. So we usually take the difference in refractive index between water and lipids for granted. We think the 1.33 as refractive index for water in the visible spectrum is a physical constant. But in fact, we wanted to ask a deeper question, which is, what gives rise to these different refractive indices of these materials in the first place? It turns out that both water and lipids derive their different refractive indices in the visible spectrum from their different absorption properties in the ultraviolet. This may sound a little bit counterintuitive, because we know water is perfectly absorption-free, at least in the visible spectrum. If you look at the glass of water in front of you, you will realize it's perfectly transparent, it is colorless, but this only implies water has no absorption in the visible. Water actually is strongly absorbing in the ultraviolet, and so as lipids. It is the difference in the absorption properties in the ultraviolet that leads to their difference in the refractive index in the visible spectrum via the well-known Kramers-Kronig relations, and can also be understood by looking at a simplified Lorentz oscillator model. So this model tells us, if we look at the water molecule, we know it's made of two OH bonds. Both OH bonds contribute to an intense UV absorption at around 100 nanometers. While on the other hand, lipids actually are enriched in CO bonds. These CO bonds have a longer absorption wavelength, usually around 250 nanometers. Now, this only explains why water and lipids have different absorption locations in the spectrum, but doesn't explain why they have different strength of absorption. Now, looking at the equation, especially the second equation on the bottom right, which is actually a simplified form of the Lorentz oscillator model, if we plug in this resonant frequency corresponding to 100 nanometers or 250 nanometers for water and lipids respectively, then we realize for water, because it has a higher resonant frequency at such short wavelength, we achieve a lower permittivity, which is epsilon, and also a lower refractive index in the visible spectrum. While now lipids, with a longer absorption wavelength, which corresponds to a lower resonant frequency, because that appears in the denominator, now we have a higher permittivity and also a higher refractive index. This explains why water has a lower index in the visible, while lipids have a higher index in the visible, which eventually contributes to scattering and also opacity of the tissue. This understanding apparently also tells us a way to engineer the refractive index and engineer the transparency of the tissue. Now imagine I have another absorbing molecule, which absorbs at even longer wavelengths than lipids. This absorption happens at 400 nanometers. It will necessarily carry some color, and you may imagine this is a dye molecule. This molecule, because it has even longer absorption wavelengths, correspond to an even lower resonant frequency, the refractive index is going to be further increased. Now, mixing this dye molecule into water by dissolving it within, you will be able to achieve an aqueous solution of this dye molecule that is as optically refractive as lipids, but then this is still an aqueous solution. Or in other words, we can engineer how much light is bent or refracted by aqueous solution simply by introducing an absorbing dipole into this aqueous component. So with that, we have demonstrated that we can start with a scattering phantom that mimics the scattering property of the biological tissue, as you can see from the far left image in the top row. That phantom is made of dispersing high-index silica particles in a low-index aqueous hydrogel. Because of this index mismatch, we know it generates scattering, it blocks light. That's why the pattern underneath is completely obscured. But now, soaking this hydrogel phantom in the increasing concentration of this dye solution, which is actually the same dye in this bag of Doritos, that's why it looks red, we notice two important things. First, the thing becomes more and more red, which is as expected. But in the meantime, we're actually seeing it becomes more and more transparent, which is really counterintuitive. Because if you imagine, if I take ink and put into water, the more ink I add into water, the less transmissive light is through this solution. But this is quite the opposite. Now, by making a medium more absorptive, we're actually achieving a greater transparency, but only leveraging the fact that the transparency is happening at the redder region of the spectrum, while absorption is actually at a shorter spectrum, which is more bluer, is a bluer region of the spectrum. So this phenomenon is completely explainable by the Lorentz oscillator model in the previous slide, and also confirmed by the FDTT simulation, as you can see from the bottom. Now, taking this dye solution, we could actually turn that into a hydrogel, and we massage this onto the skin of the animal. The first experiment we did is we shaved the hair off the mouse head, just like me, and then I massaged this dye molecule into the scalp. And then what we have realized is actually we have found is really fascinating. We realized that we could see the blood vessels, as you can see on the right, in the brain through the intact scalp and the skull, using a technology that is called laser spectral contrast imaging, which typically can only see things within the scalp, not anything beneath that. And the most interesting application of this technology actually comes from massaging this dye molecule not in the scalp, but actually on the abdomen. So this shows a shaved mouse abdomen. Imagine I'm the mouse. I'm doing this. I have the chest and the belly shaved. And then typically this is what you see. The scattering would completely obscure all the internal organs because the tissue is opaque. Now if we take this dye solution and we massage into the skin, we could actually see a lot of the organs very vividly through the intact skin, revealing many features such as the liver, the intestines, as well as the bladder. I want to convince you that this is actually a live animal. Now you can see this mouse actually has a completely transparent gut. You can clearly see the rib cage, part of the liver, that's the dark part, and the white stuff is actually its intestines and also the fat pads on the side. This mouse is freely moving with its transparent gut, does not seem to be bothered by this, us visualizing, trying to peek into its belly. So, thank you. So we were also able to use this to microscopically image the neural activity. So we were able to actually also visualize the gut motility by looking at neurons expressing fluorescent proteins through the transparent gut. And this allows us to not just perform this macroscopic imaging, but also microscopically realize what's going on inside the gut and then look at how the gut activity is connected to the brain. So this approach is reversible. You can apply dye molecules to achieve transparency at 10 minutes, and then you can extract dye molecules from the skin by using water, and this would return the skin to the original opacity. You can apply this approach multiple times. For example, you can apply it once, reverse it, and next time you need it, you can do it again. So basically, whenever and wherever you need this transparent window, you can apply this approach. So since the publication apparently attracted a lot of attention, even made its way into comics, as you can see here. So maybe next time I wouldn't need the video. I would just do the demo on myself. But then what is actually on a more scientific note, what we really are excited to find out is how quickly people adopted this approach to enable new applications in their own fields. For example, this is from Cynthia Tall's lab, a lab of a leading ophthalmologist. They have applied this to the eye, especially to the white part of the eye. They could actually make the white part of the eye as transparent as the lens and the cornea in front of the eye. They could use OCT imaging to actually image right into the eye using tyrosine. Another group, this is Adam Wax's lab from Duke University. They have applied this in live animals to enable the deep tissue OCT as well as the photoacoustic imaging. And I wanted to show you a last example is a group from China which have applied this dye molecule in the live animal, but not on the abdomen, but on the back. They could clearly visualize the spine and also the spleen from the live mouse with naked eye. So looking ahead, we think this really enables a lot of exciting new applications. Not limited just to tartrazine, this dye in the Doritos, but could also be enabled by synthetic new molecules that can achieve the same effect with less color, but also with a more safer concentration. So looking ahead, we really envision a wide range of applications ranging from photodynamic therapy in the deep tissue without surgery, and also using a much lower laser power to achieve tattoo removal through the transparent skin, as well as enhancing the visibility of the veins to benefit venipuncture, because I know this sometimes can be really inconvenient, and also deep tissue mouse imaging in the research setting. So before I close, I'd like to thank all the students who did the hard work as well as the funding sources, and thank you all for your attention.
apologize. I want to make sure you also all have time to talk with each other at the break. And so we're going to pause and not do questions now. And I'm sure you can find him throughout the day. Our next speaker is Professor Andrew Mannix. Andy began his materials science education training with his undergraduate degree in materials science at the University of Illinois Urbana-Champaign. He then moved on to do his graduate studies at Northwestern, and he was the Kadanoff Rice Postdoctoral Fellow at the University of Chicago. There, he really helped to pioneer the new types of synthesis and characterization of 2D materials that have really unique structure-function relationships. He joined Stanford here in our Materials Science and Engineering department in 2020. He's part of the reason our average age keeps slipping down, which is lovely. And for his creative work, he has earned several accolades, including the National Science Foundation Career Award and the Office of Naval Research Young Investigator Program Award. Please join me in welcoming Andy to the stage.
Good morning, and thank you all for being here. It's really an honor to have this opportunity to present at the Nix Lecture. And it's also an opportunity to follow up on Gosong's amazing talk. I will be not sharing, rather I should say, instead of talking about these Dorito chips, I'm happy to tell you about the future of a different kind of chip that I hope we all find to be interesting and potentially useful to us. That is to say, new types of microelectronics and semiconductor materials. So my research group works with atomically thin materials, attempting to achieve the very physical limits of what we can do in terms of structuring matter. And by using atomically thin materials, we view this as an opportunity to control critical dimensions and to achieve excellent properties at length scales that we thought previously impossible. So this sort of diagram here, if you will, this cartoon, represents an aspirational goal. How can we develop a sort of manufacturing process that scales down to the atomically thin limit? And so I'll tell you a little bit about the progress we've made towards that today. But first, of course, it's natural to ask yourself, why would we care about such a thing? Perhaps it's a little bit esoteric. Well, as it turns out, we're already living in the atomically engineered regime, whether we realize it or not. The ubiquitous electronics that are in all of our pockets, in fact, require a high degree of precision in the engineering of the interfaces. So really, this is just an evolution of a trend that has been going on for quite some time. At the same time, it's exciting to think about how we might start to integrate new modalities into our familiar semiconductor devices. Indeed, we may be able to reduce the energy needs of our microelectronics by factors on the order of 10 to even 100 times, depending on the application, by being able to layer materials directly on top of one another, reducing the length of circuits that would otherwise be responsible for dissipating a lot of energy. Likewise, it's fascinating to think about how we might be able to combine different types of functionality, leveraging materials, for instance, that have light emitting or detecting characteristics, better sensors, quantum applications, so on and so forth. All of these things depend upon the atomic scale details of matter, and thus we want to have a platform that inherently gives us atomic scale control. And we have such a platform given to us, fortunately, by nature. If you take, for instance, the material graphite shown here, each of these individual layers that comprise the bulk graphite structure is a honeycomb sp2 carbon sheet. And these sheets have very strong in-plane bonding, but very weak out-of-plane bonding. As a result, it is possible to thin the material down to a single monolayer and When one does so, we realize extraordinary properties. Electrons move through it almost at the speed of light. At the same time, it's one of mechanically the most strong materials ever measured. And so already we have a lot of excitement for this class of materials. And it turns out that graphene is not alone. In fact, there are hundreds of known two-dimensional materials and thousands that are predicted to be stable. And so within this vast expanse of different materials, we have a number of properties that we can realize. Anything from metallic materials to insulators with a wide gap to narrow gap semiconductors and everything in between. And so therefore, we can imagine now taking these materials and selecting them layer by layer and building up circuitry that inherently gives us angstrom scale control over the structure of our materials, while at the same time, these being thin film materials, they're amenable to the same kind of lithographic tricks that we've used for decades in the semiconductor industry. Thus, we can imagine mapping some of our understanding in principle to this platform. At least so goes the aspirational goal. However, for all the excitement that these materials have generated, perhaps sort of kicked off in part in the broader discourse by the Nobel Prize in 2010, awarded for the discovery and physics associated with graphene, there's still a lot of challenges that we have to overcome. And one of the most notable is that still today, 2 decades later from the first publications on graphene and most other two-dimensional materials in the world are still isolated the same way that they were back in 2004, which is to say using ordinary office supplies. So it really is almost an arts and crafts exercise. You take a piece of Scotch tape, literally Scotch brand Scotch tape often, and you take a crystal of graphite, which just looks like a rock essentially, and by pressing the tape into it and peeling it away, you rip away some of these crystalline layers, and then by taking that piece of tape with the layers and pressing it onto a silicon substrate and peeling it away, you leave behind some atomically thin pieces. And if you look at it, it looks sort of like a stained glass abstract art. But actually, this is because it is sitting on top of a silicon wafer with some oxide of just the right thickness to enhance the visibility of the monolayer. And so using this very elegant and simple and low-cost technique, you can find a single atom thick sheet. So that's great, but as it turns out, because this concept really democratized the spread of graphene, it also has made it much more challenging to gain a foothold in the synthesis of large area films. And that is because a bulk crystal suppresses the formation of a lot of point defects, whereas when you're trying to grow a single monolayer, that's much more challenging. Nevertheless, we have to do that if we want to make these materials technologically relevant. And so today I'll be telling you a very quick sort of montage of the sort of work that my group is doing in order to try to make atomically resolved engineering with 2D materials a practical reality. I'll talk a little bit about versatile synthesis techniques, followed by some interesting polytype control. I'll share some of the mechanical tunability in these materials, and then I'll tell you about how we can automate the process of assembling them. Now, I know I only have 20 minutes, so I'm going to go pretty quick, and I apologize for that, but I'm very happy to talk about some of this later. At the same time, I'm a little bit bummed out because I won't have time to tell you about some of the recent advances we've made, for instance, observing record-level high current density in our monolayer transistors, or achieving spatially precise doping control, because I've been told that for IP reasons, I should just keep this off of the broad public stage. But if this is the kind of thing that interests you, well, we're always looking to collaborate. Okay, so I'm going to be talking a lot about transition metal dichalcogenides, TMDCs, materials like molybdenum sulfide or tungsten selenide. These atomically thin semiconductors are much like graphene in that they have a layered parent material that serves as the prototype, and we just isolate individual layers of them. And you may be saying to yourself, why are these materials so particularly relevant? Well, it turns out that when you take a material that is three-dimensional, like silicon, and you shrink it down to nanoscale thicknesses below about 3 nanometers or so, you start to see that the mobility, the charge carrier mobility in silicon takes a nosedive. And that's because the disorder associated with that three-dimensional crystal being shrunk down, the sort of surface roughness scattering of the carriers, means that it will not be very efficient for charge to transport through it. Whereas these atomically thin materials, absent any dangling bonds on their surfaces, have a much easier path for electrons. That being said, there are a number of unique new challenges that emerge within this field. Things like, for instance, the need to grow better films, the need to reduce the electrical contact resistance. After all, how do you make intimate electrical contact to a material that has no bonds that want to form on its surface? And finally, how do you automate the process of fabricating these painstaking structures? So we'll talk about synthesis first. The most common method is to use powders in a tube furnace. And if you heat them up in just the right sequence, you end up with a nice monolayer film, but it's often irreproducible, or at least it's kind of hard to dial in. You can also use a purely vapor phase chemical vapor deposition approach using metal organic precursors. And what we did was bridge the best of both worlds, developing a hybrid MOCVD technique. This technique gives us the flexibility to both try many different compositions without having to engineer our gas delivery sources, but at the same time gives us consistent, reproducible, high-quality crystal growth. And this has given us the ability to experiment with chemistry. So, for example, we can take an aqueous solution of a tungsten salt plus potassium hydroxide, which I'll explain in just a moment. And by coating that, so let's say spin coating it onto our wafer and sticking that wafer into the furnace and running this sort of sulfurization process, we can get wafer scale films of high quality. We see, morphologically speaking, that it is what we would like to have. This is a partial monolayer film. And I'd like to particularly note that in this atomic force microscope image to the right, you see that, in fact, the surface is quite smooth and free of particles. And that's great because if these materials are dominated by their interfacial behavior, then we need clean interfaces in order to do fundamental science with them. And we see pretty good transistor characteristics out of these too. With essentially no optimization, this is one of our first papers with this material, we see respectable on currents, let's say, for instance. And so in short, it's a really great platform for doing versatile chemical exploration, but that allows us to answer some really cool questions, like say, for instance, why did I include potassium hydroxide? Well, it turns out that when you add these salts like potassium hydroxide or sodium chloride, it's sort of like the secret sauce that makes these materials grow into really large crystals. And so this is an innovation that our friends in industry are a little bit frightened by because they don't want us to be putting potassium or sodium into their pristine facilities. So therefore, we have to figure out chemically, why does this work? Why can you grow much better crystals at lower temperatures using this technique? And so that's something we're working towards. And in the process of trying to understand that, we found something really cool, which is that we can grow ferroelectric two-dimensional semiconductors essentially by making a sandwich in the reactor and sort of confining the precursors, forcing them to interact for a little bit longer. It seems that we get a very phase-selective growth of a new two-dimensional film that is ferroelectric and thus is going to give us some new functional characteristics. So all of that is building towards us trying to use our own home-built reactors to grow materials at the 4-inch scale, wafer scale, which is large enough to make thousands of devices. And we want to then use that to understand the practical aspects of engineering high-quality crystal growth. One thing that we found, for instance, though, is that it's really hard to make devices on every wafer. So we developed hyperspectral microscope techniques, essentially taking a snapshot of a bunch of different wavelengths, stacking them together, extracting spectra from it, at each pixel within the image, and then using this to map out the defects that are present or the optical response that allows us to infer the alloy concentration or the dopant density. So this has been a really versatile high throughput technique to understand these materials. In the process of making our devices, we've also solved some interesting mysteries. For instance, for a while in the field, people have been using nickel to make electrical contact to these materials. But that makes no sense, really, when you look at it, because nickel does not align very well with the conduction band. And these are typically N-type materials, these sulfides. At the same time, nickel also is known to cause a little bit of lattice damage when it lands on the surface. So why should nickel be so good? Well, it turns out that one key hint comes from the fact that nickel is well known to be stressy when it deposits. It deposits under a state of stress, and as a result, it turns out that we can mechanically modify our 2D film. And this is something that's super cool because unlike your conventional thin films, which are epitaxially, say, bound to your substrate, this material with zero dangling bonds there is very easy to strain, to apply strain to. And as a result, we see that if we have a wide contact, a wide electrode versus a narrow electrode, we would expect to see a very different strain profile. And in fact, we see that in our wide electrode devices, which are going to have more strain applied to them, they have much better performance, almost 3 times as good as the ones with the narrower electrodes. So this demonstrates that strain engineering is really a powerful tool in engineering these materials. It also shows us something really important about benchmarking these materials, which is that you have to take everything into account. You can't take it for granted that the electrode isn't going to perturb your material in this way mechanically. But I should also note that because we're straining the material, we're modifying its band structure. And so now we're investigating this as an opportunity for quantum device engineering, generating quantum wells essentially using these mechanical strain gradients. Okay, so I know that I'm running near the end of my time, so I'm going to speed up a little bit, and I apologize for that, but I want to be conscientious of our poster session where you'll get to hear about all of these amazing things and more from our department and from the students in my lab. So I'll just say, for the sake of interest, that we would like to be able to automate the process of producing these stacks. There's a lot of cool stuff that comes from this. If you can twist the interlayer crystal orientation, then you can generate this tunable periodic potential. And if you choose so-called magic angles where the electronic structure, the band structure adopts a so-called flat band. This flat band essentially drops your carrier velocity to 0 effectively. As such, the carriers are forced to interact very strongly with one another. You're essentially making a strongly correlated system out of something that has no business being so strongly correlated. And it seems that this principle applies very widely to 2-dimensional materials. It's not just graphene, but graphene was the first, and so far arguably the most successful. But it turns out that as you add more layers, each additional layer to this structure adds new interesting flavors of physics. So each one adds new subtleties to the symmetries being probed, and thus it's really interesting to explore multi-layer assemblies as well. Unfortunately, as I mentioned earlier, when we do the Scotch tape method, it's quite unruly. And so this process of assembling it is also quite manual. It's essentially an artisanal process. Skilled grad students going in there with these micro manipulators, grabbing these individual little crystal flakes one at a time. And as a result, you get massive variability both from person to person, from device fab to device fab run. And these are very tiny devices on the order of only like 10 microns in size. And if you look at this example from the literature, for instance, we see that this interlayer twist pattern, this moire, varies a lot from one side of the crystal to the other. And that kind of heterogeneity is something that we can't afford in our electronic devices. So what we'd like to do then is automate this process, make it systematic using both wafer scale growth and using automated assembly tools. And so I'll just show you a little bit of how we do this. Essentially, we have a robot inside of a vacuum chamber. We can tell when it's touching the surface because it changes the color under the camera. And so here's a video of it picking up a bunch of pre-patterned little sort of Tetris block shaped bits of 2-dimensional molybdenum disulfide semiconductor, so that at the end of it, we have just a structure that varies from 1 to 16 layers in thickness. But of course, we can do this with much more complicated structures, and we can use this, for instance, to also engineer new crystal interactions. By taking pieces of a single crystal, for instance, we can look at the fascinating dynamics of the lattice reconstruction that emerge in this 4-layer stack. I'll note that these sort of satellite peaks that emerge in here are not expected, and that was quite exciting and surprising to us. But you know, I will omit the details for the sake of time. But I'd like to say that we can engineer now new crystals that are chiral at the fundamental atomic scale in a way that would never be allowable by nature, and that can combine many different materials in order to achieve this. So lastly, I'll say that it's really exciting for us to be able to make these materials, but it's also important to have quality control. It's important to know what we've made. And that's because when you have variations in twist angle, you also have variations in properties. So we developed a technique that allows us to image not just the moire lattice, but also the atomic lattice in these. And that allows us to understand them better. And so now building towards the future, we're looking at trying to apply this wafer scale growth, these metrology techniques, and the ability to fabricate things under ultra-high vacuum, the very conditions responsible for the most pristine semiconductors known, in order to improve the quality of this interfacial assembly. And so looking to the future, we're quite excited about our opportunities to realize new quantum devices. And so with that, I'd like to thank you all for your time today, and thank the people who make this work actually possible, my hardworking students and postdocs, and our wonderful collaborators. So yes, with that, thank you.
We'll take 1 or 2 questions if people have them from the audience.
Yeah, just a question from the ultimate fabrication aspect. Mm-hmm. How do you envision this being something that could be applied in the wafer scale? Like, you have a 300 millimeter wafer and you have all these little crystals. How do you get them into the end product?
Of course. Yeah, that's an excellent question. Although I've seen some clever conceptual proposals to make this a reality, in practice, I think that it is necessary that we get thin film growth working. And so if we can grow thin films of these materials with layer control and with really high crystal quality, then I think it's quite reasonable to expect that we would be able to assemble these using techniques that are already being developed for heterogeneous integration of different materials. So stacking 3-5s onto silicon, say, for instance. The technology already exists. We just have to readapt it for this new purpose.
Great. Well, then please join me in thanking Andy again.
So this year we decided to do something different. Rather than having another scientific talk, we have a panel. Our panelists are all alums of our department. And this is designed to give you a flavor for what happens outside of academia once you leave our department. The panel will be led by Professor Yi Cui. Yi Cui is the Fortinet Founders Professor in the School of Engineering. He's also professor in the Dorr School of Sustainability, and he will be introducing the panelists one by one. Yi, the floor is yours.
Good morning, everybody. It's my great honor to moderate this session. Alberto, this morning when you showed the age of the department faculty, for many years I was so proud of below the line. Now with our new faculty joining, my God, I'm above the line right now. Hopefully this above the line also means I have a little bit of wisdom to share. Utilizing this panel, inviting our much younger alumni to have a discussion on entrepreneurship, on investment. Why don't we invite all the panelists? Let's all sit right here. Then I can give an introduction one by one. Please. I will be sitting right here. Free to take any seat. So, well, let me do a quick introduction to our 4 distinguished alum. These 4 people right here really cover our program as a representative with PhD degree, with a master degree, with undergraduate degree. So we select this panel. It's actually based on their achievement. You look at them, they're still very young. But look at what they have achieved. That's incredible. Let me start by introducing Brian Hardin. Brian come to Stanford. I think at least you were admitted to Stanford the same time I joined in Stanford, about 20 years ago. So yeah. Brian come to Stanford, want to work on one thing, very focused, solar cells. He joined in Professor Michael McGee's lab, working on solar. Before that, he already had quite extensive experience working on solar cells. So he's one of the students I often made fun of during my assistant professor time. I remember, I say, Brian, where's your first paper? Did you publish your first paper yet? I didn't know. This built really strong resilience on Brian. When he published that Nature Materials or Nature Photonics paper, he printed out, he was looking for me. He wanted to show his publishing first author, Nature Sister Journal. I was out of town for a week. That must be hard on you, and looking for me. So Brian did really well. After graduation, he founded Plant PV and taking the company to the next phase and later acquired by Hitachi Chemical. He's a serious entrepreneur. He's funding a few other companies at this moment. Look forward to the discussion with Brian. One thing I'd like to mention, Brian really want to return his contribution back to department to Stanford. So in 2019, he was teaching a graduate level course on solar cells. So that's Brian. And next person is Lu Zhang. Lu joined in our master's program. I still remember teaching a class Lu was taking. And Lu was very, very active already in the department at Stanford during her time here. I believe you briefly worked with Jim Plummer. I think Jim is somewhere in the audience. So after graduation, Lu founded her first company and quickly got acquired and quickly turned into a person doing investment. She established her own venture fund called Fusion Fund, specializing in early stage investment in enterprise AI, healthcare AI, and industry automation. I interacted with Lu quite a bit over the years, and she has amazing insights and knowing what's the most exciting industry, what areas to put her investment on. She has accumulated quite a bit of honors, and she was honored as a young global leader by World Economic Forum, the Davos Forum. She's also honored as a Silicon Valley Women of Influence, top 25 female early stage investor by Business Insider. She's also honored with Forbes 30 under 30. So she's a truly entrepreneurship influencer. Next person, Andrew Burns. Andrew is very dynamic from his smile, you can already tell. I still remember you taking my class, and you are the person walking into the classroom, have a lot of communication back and forth. So that's why I remember students. If students reach out to you more, you remember more. I told all my students, I say, go talk to professors. Don't be afraid. Then these are the list of people talking to professors often. That's why over my 20 years, even though none of them work directly with me, I remember them for a long time. So Andrew is currently serving as the director of Micron's AI fund, doing investment in supporting early stage AI startup. Before that, he was the founder and CEO of Stow Energy, an early startup leveraging machine learning to provide predictive operation for distributed energy systems. He has his master's degree from material science here. Next person, Sharon. Sharon worked with Professor Sarah Hershon in her lab. Before joining her lab, I think I served briefly as your academia advisor when you were a Stanford freshman. Sharon, let me mention the award she won. And it's the highest award in engineering school in 2016. She won the Thurman Award. I checked online last night. Basically, I think probably each department only has one, maybe even less than one each year to win that award. That must mean you have very high GPA. That's usually the case. So after Thurman Award, she has quite a bit of experience. She was actually working in Carbon for, 5 years. Carbon is a 3D printing company. And I'm still having a shoes, I think printed by Carbon, is Adidas with that 3D printing, very comfortable. I remember Sharon, while working in Carbon, you just come out of Carbon and ask your questions. probably 4 or 5 years ago. I said, Sharon, what's the biggest lessons learned through your industry experience? I have all this materials technology. I want to get some advice from outside. She told me one thing I still remember. Guess what? No matter how good the performance materials will be, the customer, the first question they ask is, what's the color of the shoes? That really made me think, let me recalibrate myself a little bit, right? We got to combine material science broadly with from customer's angle. So and it's, that conversation I still remember for a long time. So afterwards, she spent a year in Beijing as a Schwarzman scholar. And then coming back, she served as Director of Global Business Development Baichuan Resource Recycling. Most recently, Sharon is a venture partner in Revent. This is a venture capital firm. All right, with this quick introduction, let me ask you the first questions. We have a lot of students right here, current students. So first, why do you guys choose the career path you have been on? What's really driving your thinking? What's been motivating you? We can go this way. Maybe Andrew, start from you.
Sure. Yeah, I was just talking before this about like serendipity and like the journeys in scientific discovery. Startups, I was a founder and I've been investing in startups for the last 8 years. It's really hard to be an entrepreneur and like start a business off of these innovations that were like pulling out of our academic pursuits. And I was thinking about this question, and the only thing that came to my mind was a Bon Jovi lyric from Living on a Prayer. It's like you live for the fight when it's all that you've got. Like I really like fighting, and I love fighting with like small teams that are trying to do stuff really hard, where the rest of the world is like very dismissive of like these efforts. And like honestly, I think that's it, right? Because like money is great. Notoriety is great. Being on a stage is super fun.
As far as I can tell, all the faculty in the department, we are not fighters. We are very nice. How do we teach you to become a fighter?
Oh, it wasn't you. It wasn't you. It was Alberto. But yeah, it's like that's the thing that like gets me up in the morning. It's like let's go to work. Let's go to battle. And with the founders that I invest in, it's pretty awesome.
Brian.
Yeah, I mean, in terms of motivation, like I think it goes for me to like in high school. So I had a really crappy car in high school. I grew up in Dallas. It was like a 1972 Triumph Spitfire, and it broke down every week for like 10 weeks, and then once a month indefinitely. It's still in my mom's garage. But my dad and I built a portable solar-powered air conditioner for it because it had none, and I lived in Dallas, and it was pretty hot there. So I looked at that panel. I was like, man, can we do a better job, make a more efficient panel, make a cheaper panel? And that got me interested in engineering. And I went through Texas, Oxford, EPFL, and then Stanford, all just trying to make better solar panels. And then, and then after that, it's like a really interesting time to go and try to apply that knowledge on a more industrial scale. And so I started my first company, and now I have another company that works in material science for solar. But yeah, if I didn't do solar, I don't know. Like it's really, I'm very interested in like taking things that are winning and like help them win more. And I think like solar and batteries are two very interesting areas where there's lots of opportunities.
Lou.
Yeah, so I have many people ask me why I initially chose material science as a major. It's really went back to when I was a little kid. I grew up in my hometown. It's a place called Inner Mongolia. Lots of people even never heard about the place, but it's a beautiful place with a great culture, great nature, but we don't have technology innovation. But I still remember when I was a kid there, I saw the science fiction magazine talk about how to build a space elevator. If you want to build a space elevator, you need the hardest material theoretically in the Earth, which is carbon nanotube, which kind of contribute to my research in undergrad 4 years in carbon nanotube. It was great to publish paper, but I was thinking about how to also make it faster in terms of commercialization. So I came to Stanford. One thing I feel really rewarding is that Stanford provides such a diverse option of you can choose different subject, different research project. Some are may long term, 10, 20 years, what's going to happen in the industry. Other direction, you can, like solar, you can make impact to the industry right away and make commercialize the product and also company. Another two things really make me continue to do, initial was doing research and later entrepreneur, eventually so-called went to dark side, started my own VC firm. I think one thing actually I remember Professor Trey always talk about is to change the world, create a fortune, but the most important thing is to change the world. You can do it by creating a company. Also can do it by investing in great company and be a long-term partner with the founder at the earlier stage, go through the most, I would say, miserable, vulnerable stage and help them accelerating the growth. And also fundamentally, the reason I choose the vertical I've been investing in the past 10 years, also come back to the root of material science. What is the problem we're solving by material scientists? It's always the hardest problem. We got exciting, identify the hardest problem, try to solve the hardest problem and create a potential solution and make it commercialized ready. So I think that's kind of what keep motivated me, continue doing what I'm doing, and also be excited about all this new technology innovation happening in the market.
Sharon.
And I'll just add my 2 cents. I have a philosophical answer, but I have the real answer, which is I wanted to be an econ major, and then one day I was sitting in the back of an econ seminar, and Professor Cui was a guest lecturer, and I sat there and I saw slides on nanowire battery materials, and the next quarter I enrolled in actually Sarah's intro to math sci class, and I was hooked, and I still think of that moment as a great turning point, and it's just serendipitous. But if I had to give an answer of why, not why I chose, but why I continue to love this field, there's this saying of great societies or great civilizations are civilizations where one generation plants trees whose fruit will only be enjoyed by the next generation. And I think in the field of engineering and science, material scientists are the tree planters, right? I think in many, many instances, it's like a materials breakthrough that happened like decades before that paved the way eventually to, I don't know, iPhones we have today, to, why can we build wind turbines in the ocean? Because there was like this anti-corrosive like coating that someone developed so that you could actually put metal in highly saline environments. So yeah, that's how I think about this field, and that's why I continue to really love it.
I love to take the credit to convince you into material science. Now I remember, you serve as a volunteer. When I gave that seminar to a bunch of CEOs, you serve as a volunteer. You see the backside of the room many years ago. Now I remember. I took the credit. So let's talk about first questions. Materials technology related, manufacturing, and Lou, I know you invest a lot in AI, but you have been watching the whole manufacturing going. At Stanford right here, over the past particularly 3-4 years, there's a lot of discussion, how do we take technology to scale? Will Chu and I have been chatting a lot about that. Will is teaching a class on scaling of sustainability technology. Talking about scaling, without scale, you will not have big impact globally. Brian, particularly you on the solar area, you have a lot of experience. Andrew, you look into, I know you look into water, you look into other areas of investment. Lou, you have been watching this. Sharon, you travel back and forth between here and Asia. So any wisdom to share? How do we do global impact, scaling a technology with the low cost in order to make an impact with low cost in mind? Without the cost, scaling not possible. Anybody want to jump out first to share your experience?
I'll go. I think, so I did my startup out of my master's program. And I thought maybe about 5 minutes on what I was going to build, and then I went to the D school and launched a startup, and I spent 7 years of my life doing that. I'd say it's like if I were to go back in time, I wish I would have spent more time thinking about where I am in the evolution of technology trends and adoption rates of new technologies, to be able to build something that hit that intercept point in the next 4 or 5 years or whatever I was starting from. At Micron, so I help run the venture fund for Micron, and we have a big program on, hey, how do we ingest new sustainability tech into our legacy industrial systems, our big fabs. That is hard. That is really hard stuff. But I think if you're thoughtful and you understand where to bring your technology in and these intercept points, I think you can create this opportunity to accelerate new technologies into larger industrial applications. And then your experience is probably different from ramping new manufacturing.
Yeah. Well, it's kind of funny because E was an abusive older brother to me when I first came in. He was a professor. His first year was my first year, and Alberto and him came in at the same time. Alberto, you were the nice big brother, but it's been fun to watch E evolve as well. And so when E first came in, he was really obsessed about publishing science papers, and then he starts Amprius. And then I remember a few years after Amprius, he's like, yeah, academic papers is 10% of the way there. The rest of it is really manufacturing and customer development. And I think that's entirely true. And what I would say about scale up, it's very hard to do in an academic setting. And I'd say that my hack for that is if you work in a really important space, a problem space for a customer, if it's a top 3 concern for the customer, and I work in solar, so silver usage is the #1 concern, you can find customers that will test with you very aggressively. And so in my first business, I was able to spend very little money just by flying to China 1 week a month to work with tier 1 solar cell manufacturers. And we built good relationships, and that's what I do in my current company as well. And so you can leverage the infrastructure around you if you work on problems that are meaningful. And so I would say that when you're thinking about this as grad students, I think it's very important to do good research, but also be thinking about what are real problems in your industry.
Yeah, to add on to it, I think sometimes it's a chicken-egg problem. If we have a better geopolitical environment right now that we could leverage the global supply chain to lower the cost of the technology and make it more sustainable, easy to scale up. Unfortunately, sometimes technology innovation trend is different from the political side of the trend. But on the other side, I think the silver lining of this situation right now is a large corporate, including you mentioned about Micron and lots of other large traditional corporate, they're really eager to integrate with new technology. They also start to realize it's actually harder, take more capital, take longer time for them to develop a new solution in-house. Instead of doing so, they are more open to allocate bigger budget, either to corporate venture fund or to the CTO, to collaborate with a startup company and integrate their solution with their existing supply chain manufacturing and go from there. So that's the reason for us. First, we have to acknowledge hardware is hard. Anything related to hardware is very different from the scaling timeline of the software company. But on the other side, if a founder or technology owner can be smart to build up initial partnership, and also find the right partner to co-develop and take it from there, it will make the initial capital-intensive phase slightly easier and also take a shorter time to scale up the technology. So I think that part is really important for founder to realize it from the beginning instead of thinking about, I just focus on technology myself until later I start to look at who's the major player on the market. Understand the market landscape is very important. And meanwhile, another thing beyond there is really about how you design your solution. When we talk with lots of technology owners, we also invest in semiconductor. I was always joking that because I'm material science background, I'm very picky on company focused on solar, lithium, battery, our chip. But we still invest a couple of chip company. One thing we found founder did really well is they're not only focusing on how to make my technology cheaper, but also think about how to make the integration cost of my customer cheaper and faster. So when I'm presenting my solution to the customer, they found it so easy to plug and play and go from there. That means sometimes you may need to compromise your technology specs a little bit. downgrade a little bit to go along with your customer's infrastructure and upgrade together with them. So there are lots of things are happening in the industry right now, make it a better environment and ecosystem of hardware innovator to go from there. Still, we know this is the hype about AI. There are lots of discussion about the AI plus hardware. Physical AI is also the hot buzzword here. So we're just hoping to do more education to the industry and then support better founder in the hardware domain to go from there.
Sure. This question, I just think about so much. And actually, just to add on, there are so many founders on this stage, and as of last month, I am happy to have, while wearing also an investor hat now, started my own company, exactly trying to address this problem of how many materials innovations are there that just never see the light of day and never actually have at-scale impact that we describe at the opening first 2 paragraphs of our academic journal articles, right? This is the future vision that my work is going to produce, and it just doesn't necessarily come to fruition. And I think the two data point, or one anecdote and one data point, I guess. When we were studying batteries in school, and there was always this, at what point will batteries finally make EVs happen, make grid storage happen, make electrification happen? The holy grail of the dollar per kilowatt hour in the battery space, right? $100. Can we hit that level? And I think when I was in school here at Stanford, it was like, I don't know, we were at 300 or 400. I don't remember the exact numbers. The standard market price now for lithium, for LFP batteries, lithium, the most common type of lithium-ion battery right now was hit $100, I think, around 2 years ago. Now it's more like 50, right? So, and this is not because some academic lab invented a new type of battery or even a way to make a battery. It's just the power of industry and having an ecosystem and having competition. And yeah, that's one data point. I think another data point around LFPs, I had one of the smartest people in my undergrad cohort ended up doing a PhD at Stanford too. He ended up working on LFP batteries in his PhD mostly, and when I first met him as he was doing his PhD, he was like, oh man, I'm working on this kind of outdated, old type of lithium-ion chemistry that no one is really interested in academia. In the 4 years, 5 years maybe, of his PhD, totally flipped, right? CATL happened. Tesla realized that, okay, in order to hit our cost targets, we need to do LFP. We need to set up our own LFP manufacturing here. And by the time he graduated, he was one of the most sought after battery scientists out here, right? He also had he's incredibly smart, had a great publication record, but he was working on what was considered unsexy in the world of academia. And turned out he might have one of the biggest impacts of a lot of people.
Sharon, while you are speaking, I saw Chu was smiling. You talk about LFP. He has a first-hand experience seeing how the cost are coming. So, yeah.
Yes.
So there's a lot of wisdoms right here. Let me maybe just share something briefly and see whether you agree. In recent years, looking at material science technology, a cost cut down, I say, well, I need to understand this. Even though I'm a faculty member here, I don't work in a company, but I have the luxury serving as the board of director for my own startup. And I visited our suppliers. And I'll tell you what, material science knowledge matters at the time. Looking at the cost right there, we say, hey, why don't you talk to our supplier, reduce this. You have the thermal process. Why couldn't you reduce from 10 to 5 minutes? Why do you use this expensive solvent? Why don't you use that solvent, water-based? eventually you squeeze the number down by quite a lot, with enough material science knowledge going right there. This is just so powerful. Just squeeze every single penny you could squeeze. Eventually, this add together to do the low cost possibility and also scaling possibility. So let me ask you guys, next question. I was thinking about this. I think everybody sitting right here thinking about this. What about AI? So AI now is just like, everybody's talking about AI. 2 Nobel Prizes last year, chemistry and physics. And all my new graduate students coming in, I think they are all studying at least 1 or 2 machine learning class. And a few students working on AI and materials combination. So I can see this could be breakthrough coming out of material science research the more we use AI. So what are you guys' thoughts on AI? Specifically, what are the most exciting AI areas? Is really coming, making an impact, a strong business case? And what do you see AI for material science? And also, what do you see material science for AI? Love to hear your wisdoms on this. Brian, looks like you're ready to.
I'm like the least qualified to talk about that. Based on this
Lou
panel.
is ready. Looks like.
I'm interested to hear your perspective.
Yeah, I use AI to make funny pictures in board meetings, and my team uses AI to speed up computer programming. So if you're, it's really great to write scripts. So like from a practical perspective, I think if you're using generative AI, what it provides you is like 80% of the solution of what you're looking for, and it gives you the most average academic, opinion, like a Berkeley professor, like whatever Berkeley professor thinks. That's what I'm kidding, but that's what it's really designed to do. I don't see it coming up with really innovative solutions. I don't think it's going to win a Nobel Prize by inventing a new chemistry or anything like that. Now, from if I'm a grad student and I'm looking at AI right now, what I would tell you is the most successful startups that make the most money are things that Mark Zuckerberg and Sundar Pichai want to purchase, because they have literally like hundreds of billions of dollars in cash. And so if you're looking at chips, if you can design a more energy efficient AI chip or a GPU, like if you can come up with new areas there, you can receive lots and lots of funding, and there's lots of tools that you can use and access and do really creative science. So I think from that perspective, I think it's a really good time to look at design, especially around energy efficiency and data communication within chips. But as like a material scientist, am I looking for a database to tell me what alloys I want to make with my stuff? No, we figured out the old-fashioned way, and I don't think it's, I can use design of experiments and get 99% of the way there.
That's awesome.
Lou?
Yeah, I will try to make it concise because it can go on for 20 minutes discussion about AI. So number one thing, I don't think it's a bubble. It is really happening. AI is bringing a new technology and it's like a catalyst, not only just accelerating the digital transformation of the industry, it's also accelerating other technology to be implemented faster, especially within the healthcare domain. Which is also one of my favorite vertical. And another thing I think we also need to be very practical is AI doesn't equal to generative AI. After we have ChatGPT, everyone think, oh, AI is a Gen AI. When I was an entrepreneur more than 10 years ago, we're using machine learning to improve the accuracy of early diagnostic of type 2 diabetes. We call it machine learning, we didn't call it AI. So being exists in the market for a long time until recent. People found out, oh, it's so low entry barrier for everyone without any coding knowledge or writing single line of the code be able to use AI. We call it no code AI. So I think that's kind of what is happening right now. And another point I really want to make is we need to distinguish between consumer AI and enterprise AI. Consumer AI, I agree with you. I don't invest in anything on consumer AI. Regardless what is the innovation going to come out, we also need to think about the differentiation is who control our access to the high quality consumer data. That's Google, Facebook, all these large companies, and how to compete with them. So consumer AI market might be dominated by the large corporate, but enterprise AI is different. That's the reason why DeepSeek make people so exciting. Small vertical model, you could build up a vertical application for a certain industry. You don't need to have a large model answer all the questions. You just need a small vertical model with all the domain knowledge retraining focus on healthcare, focus on financial, focus on material science, focus on space tech. And also the last point, we also need a human in the loop, at least in the next couple of years. Lots of discussion about AGI, etc. We're joking that the definition of AGI for academia is very different from the definition of AGI in the industry. So I think it could be treated as fundamentally a productivity tool when you utilize AI for your workflow. We see that happen a lot in healthcare industry already. Even for the space industry, we've been investing in space industry, you can see how much cost reduction being done by utilizing AI to basically streamline the whole workflow from the hardware software integration. Another thing, I think AI may bring up new opportunity for material science as well, because software could not solve all the problem right now for AI. What is the biggest problem for AI? GPU consumption, energy consumption, and also latency issue, data privacy. When we talk about the GPU consumption and the energy consumption, of course, material science is going to play an important role to help AI become affordable and in the future to deploy across different industries. We couldn't just solve that problem with a hardware layer. So we have a couple companies, they're focusing on it, using hardware solution to reduce energy consumption dramatically, 100x, reduce the GPU consumption dramatically. So I think if material scientists start to look at from that angle, that might be a really good point to combine material science knowledge with what is need to be built for AI ecosystem in the future.
Sure. I had a conversation with someone who introduced themselves as ex-Google, ex-Uber, I forget which other.
Stanford.
He was MIT, actually. And he was a data scientist. And this was last week, he told me, I cannot believe how antiquated your field is. My field being material science. This is exactly how I felt. I remember graduating almost 10 years ago and getting into my first industry role. And we were a tech company, we were backed by Sequoia, we were, going to be the Apple of material science. Yet in the lab, we were, doing lab notebooks, and we would export CSV files from a computer that, the lab software could only run on the previous 2 versions of Windows, not the current one. And it just felt like it had to be better. Right? And I know so many people in my cohort who ended up trying to crack this problem. My friend Enzi, who ended up at Citrine. There was another Math Sci grad who ended up at Uncountable. Tons of these AI for materials in the past 10 years. And last week, I still have someone come up to me and say, I can't believe this is how you guys do things. So all that to say is that it is an insanely hard problem that I think we should all be thinking about. And I think there's a lot more computational background and interdisciplinary nature throughout education now. But every material scientist coming through the door just now we need to be that baseline level of AI computation literate, or else I'm convinced that why wouldn't you want to be able to get 100 experiments worth of information in the effort that you put it into 5, And 2, it's not a problem that someone that's just ex-Uber, ex-Google, ex-tech, I know data can come and solve, because of exactly problems like in the previous talk by Professor Mannix, right? Turns out on these when you're atomic layer thick, the size of your contacts makes a 3x difference, right? Things that we're not even documenting the little process details. Sometimes you in our previous lab we used to say, oh, it's the outcome of this experiment depends on the phase of the moon. Or maybe it's the relative humidity, right? These are big data problems that I think we're just not traditionally trained to think about. And so what I would love to see is us as a material science community really, maybe we have to go deeper than what Citrine, Uncountable, et cetera, tried to do. Maybe it takes a generational change, an attitudinal change, but I'm really excited to see this next round of attempt at AI cracking the material science problem.
Yeah. Andrew, anything to add?
What was the question?
AI for AI. AI for materials or materials for AI. Is this AI this one? Is it real? Something meaningful coming?
And I'm not familiar. What does artificial intelligence mean?
Yeah. Yes, artificial intelligence. Whatever models you can see currently.
Yeah. Sorry.
Yeah,
Thank you
I know you're making
my joke. Yeah, I think it's kind of everywhere right now,
Yeah.
and like it's being deployed all over the place, like faster than we appreciate. There's lots of builders in material science. I know Will has a company. I invested in a couple material science AI for materials companies. Micron is working to scale like a bunch of interesting new artificial intelligence capabilities for manufacturing and design of next generation semiconductors. But I think it's just this really like breathtaking tool that's captured a lot of like imagination of all of us. And yeah, I don't know. I guess the response I give to this question, it's every day as a VC in this category. I've been investing in artificial intelligence since way back when in 2017. So it's super old school. But every day I wake up and I go to sleep and it's like, tomorrow can't be crazier than today was. Like the intensity of the conversation around this technology set, it can't be crazier than yesterday. And every morning I wake up and it is. And so I think it's just kind of like you were describing. It's just like it's this new capability that everybody is starting to understand how to work with. What I think is really interesting is I mentioned the design school earlier, and I'm a little bit biased because I like the D school ethos and Post-its and whiteboards. But like, how do you design this? How do you design this technology set to make it like work for us and to add value for us? If you're doing material science, how do you apply artificial intelligence to build the dreams and things that are in our brain? Again, yeah, the two-dimensional lecture that Andrew gave. I can very much see how like different subsets of artificial intelligence can accelerate his the visions that he has for what this technology set can do and how to explore and how to scale it.
Yeah. Something we see in the lab, 7-8 years ago, I was skeptical myself also, but when a professor is skeptical, then you could run a research project to try it out. So we utilize AI, the data and machine learning to help us to predict new type of solid electrolyte. With some success, I see a little bit of that, but still skeptical. But skeptical, then we continue doing that. I think recently, about 2 months ago, there's something major I can see AI has been quite helpful for us to predict new type of electrolyte for high energy density lithium metal batteries. It looks like something good is coming. I would say we completely have a breakthrough yet, but it's oriented towards that direction. That's my feeling. That's my feeling at this moment. So in about 5 minutes, I want to open the floor to questions from everybody. But I see, my son just walked in just 5 minutes ago. I want you guys to share your thought about Stanford education. He's a freshman right now.
Where is he?
Well, he's staying somewhere, so I don't want to embarrass him. So he's still high. So, and after he comes to Stanford, he said he's thinking about STEM. He's thinking about material science. I say, wow, I didn't have any influence. So he first time learned about H-index. And then after he learned about H-index, he said, well, Dad is not doing bad at all at H-index. I first time feel like I gain respect in the family. So however, the education program here, I want to ask you, we have undergrad, master, PhD, right? What part of Stanford education, in material science particularly, impacted you the most? And what you're doing right now, I mean, just going so far away, right? But there's still a little bit of linkage with material science. So what part of Stanford education that's impactful to your own career?
Yeah, I can start. I think one thing I really love a lot, especially when I look back, I have all, like, no matter it's my partners or even other founder, I was like, oh, dude, you invest in both hardware, software, you invest in both AI, healthcare. How could you get all this knowledge? When I think back, it's actually all from material science education because material science department is very diverse. Think about all the research subjects we're able to access to and work with different professors, the collaboration between different departments, and also serve as a foundation of lots of different innovation across different disciplines. I think this kind of a foundation of education give me a strong capability to digest and learn new things very, very fast. Essentially, that's critical for becoming an entrepreneur. Another thing is it's critical for becoming a venture capitalist, be able to look at different innovation very fast. The learning curve is short, and also be able to go from there. And also another thing is, I think in general, within the material science and also the engineering department, I remember that was Professor Jim Plummer mentioned, and also Professor Sinclair also mentioned, Stanford engineering wants students to become pie shape. I still remember the pie shape. It's not T-shape, it's pie shape. So horizontal is you have a very good exposure to all different types of innovation. Vertical is the depth of the technology domain. And then there's also a path for commercialization. How to really think about not only doing research, but to commercialize the research to a real life product and also solution to drive a positive impact. I think that's also something I keep thinking about it. I keep sharing that with entrepreneurs, with other students I talk to. That's kind of the thing keep me motivated me to do the innovation.
I think exactly that. I love the pie shape.
Yeah.
I think that extra one,
Yeah.
swivel, is key. My sense of my peers and my professors and everyone I've come across at Stanford is the question that we're really good at asking and is strangely not always asked is, so what? Right? Like maybe you have the H index, right? Maybe you have like really a great resume academically, but at what point do you walk around on the street and you can see someone holding in their hand, or in my case, wearing on their feet, something that you made, or something that directly came out of your research, right? I was just speaking to a fellow alum, Arthur, whose engine ended up in space, right? And I think whether it's through academia and trying to, like, whether you're in this track and partnering with industry to understand the problems that are really, like, being felt in the real world right now, and maybe you're planting the seed for generations down, or if you're trying to spin out and really make something into product, right? If we, thinking about Professor Cui and Amprius, among many other companies, and Will with Mitra, and my previous company was started now by a now Stanford professor, Professor DeSimone, Joe DeSimone. Like, the number of professors who are just trying to, students just trying to move like what you're finding and discovering into something that will actually impact and benefit the world. I think that is a frame of mind that sometimes gets lost in other academic institutions, and that's what I really value about the Stanford community.
Yeah. Brian, Andrew?
Yeah, I think the most useful thing for me was just building a lot of really deep relationships with people. And there's several of them in the audience. I got George and Ekong, we're in the same group together. We spent a lot of time. I see another like half a dozen people that I spend quality time with. And I think the best part about Stanford is just people are smart in many different ways that can often like complement you. And just to be able to have this community and to spend so much time with them and to have these events is really like the biggest advantage. Like, I did take E's class, I don't remember it. Bob tortured me in his, like it's fine, but like ultimately, like if I'm a grad student, I'm here, I think the really important thing is, like play volleyball with each other, get to know each other well. These will be lifelong friends if you do it correctly. And they will continue to help you. I talk to my friends about my businesses all the time, and they continue to provide unique insights, even if they've only heard about what I'm working on for 10 minutes. So that what I see would be like the most encouraging thing about being at Stanford.
Yeah, and so I did my undergrad at University of Arizona, which is a great school. But like I had never heard of startups and being able to build your own company. And so like that concept of entrepreneurship, it was like very siloed in the business school. And I think what's so like magical and special and like arguably unique about Stanford is that like we're looking around at our peers and it's like, oh man, that person over there is building a company. You know, and that girl over there is doing a company. And so it creates this like collective belief in ourselves to be able to like do things that everybody else in the world thinks is impossible. And I think like having that coming from like STEM colleges, it's just radical. And that's why you see so many great like transformative things is everybody here has drunk the Kool-Aid. And then there's the ecosystem around us that can help us turn like Kool-Aid into like really great, I don't know, ice sculptures of startup victory. But yeah, amazing place. I'm just glad to be a part of it.
Let's open the floor to questions from the audience.
Can I ask a question to them?
You could, yeah. Please.
I mean, like to the more seasoned elder professors on the chart.
Above the line.
Above the line.
Or stand up. Or
what do you think about artificial intelligence for material science? Sure. Raise your hand, sir. Thank you.
So your last comments really resonated with me about the uniqueness, perhaps, of this environment we have here, the startup environment. I've given talks around the country at different universities, at Purdue and Ohio State and different places, and it's very different there. Many of the students, the grad students, are focused on getting into an industry or doing something like that. I don't see this combination with the business and the entrepreneurship. Can you talk a little bit more about, have you seen build up kinds of tech hubs in other parts of the country or the world that have some of the same similarities, perhaps not all of them, but some of the same similarities we have here? Lou, you might have some ideas on that too.
Yeah, so we actually invest outside Silicon Valley as well, and some of the university even specific access. Okay, what is the best practice you saw from Stanford to create this ecosystem? For example, we also work closely with CMU in Pittsburgh. They also have amazing startup ecosystem there. But I think what is unique about Stanford is not only just the structure set up here, like tech transfer, everything. It's also really about what you mentioned about the people. You know, students being educated from day one, they think innovation is important. They also have the pure motivation or pressure, feels like everyone's trying to change the world and create something new. Another thing is professor. You know, I remember when I talked with Professor Trey, when I talked with Professor Salion about, okay, I want to do this company, etc. None of them saying that you're too young, too early. They're like, you should give it a try. Maybe you'll be successful. And also, I think this supporting system is really unique. And go beyond there is the Stanford alumni. And when Stanford student and material science student wanted to ask for industry feedback, support, fundraising, there's a strong alumni community support them as well. So I think people create a unique culture here. And also this culture have a unique value and vision, which differentiate ourselves from the rest of the country. I think everyone tried to replicate Silicon Valley, and we haven't seen a successful copycat so far. That's also the reason why all this innovation trend is starting from here.
It's also like a very stupid model, right? Like from my experience. So the last time I was in this room was at like Stanford's business plan competition, and I won $20,000 with like just like air, right? And then I went out and I raised $2 million, right? And so it's like giving young like founders with really dumb ideas, tons of money, to go and try to build it and like make those mistakes with capital. Right? It's like an uber luxury compared to the rest of the country. But again, it's just like that mindset of like belief that like there's a probability of 1 in X that this will be successful. And I think that's like this unique mindset. Around the Bay Area.
I would say the best place to start a material science company is out of the Molecular Foundry at Lawrence Berkeley National Labs. It's a Department of Facility User facility. Carolyn was formerly the facility director there. You can write a proposal even as a grad student without your advisor, and if it gets accepted, you can work out of that like $100 million facility for free and use access to every materials characterization technique in most fab that you would want. So if you're a grad student, you're thinking about starting a business, you basically don't have to pay rent there, and you can use it as a non-proprietary user. I started my first business there, and I started my second business out of there. So I did make fun of Berkeley earlier, but I'm actually a big fan of the Foundry, and I think that's a really nice place to work out of.
Brian, I agree with all of these things, yet I feel like in the past few years, like an ecosystem that has emerged on my radar, specifically in China. Yes. Makes me wonder about these things. About, yes, we're really great at going from 0 to 1, but the research coming out of China, I can't compare like quality necessarily, but it's the factory that will be scaling their innovation is down the road or a high-speed rail away, and they immediately throw not something on a pilot line, then you're on commercial, and then you just get that feedback right away. And I know, Brian, you and I have had this conversation, and I wonder how we can create more of that in a place like this, because I think we really knock that 0 to 1 out of the park. But oftentimes, like I have a friend who's building a new generation of gallium nitride power chips, and trying to find a fab here that will take a risk with them, right? And like run a new fab process with them. And it's so hard. It's like pulling teeth, right? And we can't rest on our laurels, because I think industry and scale up is really where that impact happens. So
I think the biggest reason why most material science companies fail is because it takes too long to get through customer testing, and because the customer doesn't adopt it at a scale that's sufficient to justify the investment that's put in. If you go to China, the adoption rate is like a factor of 4x higher, and the scale is insane, especially for solar panels and batteries. You just have to weigh that against potential IP risk or partnership risk. But there are good and bad actors in every country, and you can find great people to work with in Asia in particular that are just as trustworthy and friendly and motivated as you are.
Our time is getting close. Let me maybe make a couple of remarks as a conclusion. This is the panel for entrepreneurship, for innovation investment. Some of the things I've been seeing through you as example, and also many people, Will's company and others, for material science innovation to go from labs to market. If I use a linear process, but it's not a linear process, the sequence, the challenges we are facing, number one, make sure the technology is working. Oftentimes, what we publish in a paper only tell you one thing is fantastic, but to make a technology workable technology, it requires 10, maybe 20 things, all satisfy, all at the same time. That's first challenge. That's first valley of death in my mind. So 90% of the innovation die in the first valley of death. And the second valley of death is, can you make a lot of this? Can you do manufacturing of this to the cost? This is second valley of death. Within that 10% remaining, a lot of them will die also. And the third one, by the way, after you have seen all of this, you see, can I sell this? Is there anybody buying this? This also can cause the death. That's the third value. But I'm analyzing through linearly, this is what happened, but it shouldn't be linearly. This should be considered all at the same time.
Yeah.
You should talk to the customer first.
Yeah,
the biggest thing
you
that you
really
can do,
need to talk to the customer first.
You should talk to a customer first and see if it's really worth working on. If it's not a top 3 problem in your industry,
Yeah.
like you'll spend 6 years trying to make a prototype only to go to the customer and be very disappointed. So,
Yeah, top 3, and also they have budget ready to go.
yes, that's right. And you can do that without having any technology. I've done that before. You just have to sound confident.
So with that, the final note, I think this is the key message. These 3 things, talking to the customer first. Material innovation should follow that. I think our time is up. Thank you very much. Let's give a round of applause to our distinguished alumni.
Thanks, Yi, and thanks to our panelists. Now is the time for our keynote speaker, Professor Bertozzi in the chemistry department. And Professor Bertozzi will be introduced by Lu Zhang, founder and managing partner at Fusion Funds. Lu?
Thank you. It's my great honor to introduce today's keynote speaker, Professor Carolyn Bertozzi. She's the Baker Family Director of Stanford ChemH and also professor in School of Humanity and Science. And Professor Carolyn Bertozzi's research interests span the disciplines of chemistry and biology with emphasis on study of the cell surface sugar importance to human health and disease. Her research group really focusing on using the information to develop new diagnostic and therapeutic approaches, most recently in the area of immuno-oncology. And Professor Bertozzi came to Stanford after 20 years in Berkeley, came to Stanford in 2015, among the first faculty to join the Interdisciplinary Institute, ChemH, which is Chemical Engineering Medicine for Human Health. And meanwhile, she has been received many awards for her dedication to chemistry and to train a new generation of the scientists fluent in both chemistry and biology. She has been elected into the Institute of Medicine, National Academy of Science, and American Academy of Art and Science, and received many prizes, including Heinrich Wieland Prize and also Lemmerson MIT Prize. Beyond become one of the top scientists in the field, I also learned from last night a pleasant dinner conversation that she's also a serial entrepreneur. In the past 9 years, she already spin off and support over a dozen of the startup spin off from the institute. And meanwhile, she's also an active board member, really become a female leader supporting the company for both a public company and private company, supporting important board directorial to really bring in the new knowledge and to the large company's future strategy. And most importantly, she's also an amateur musician. If I could mention, I'm also a musician. I really want to highlight that. She played bass. She also played keyboard, and recently she has a new band. So I'm really looking forward to her performance in the next couple months. And without further ado, let's welcome our keynote speaker, Professor Carolyn Bertozzi.
Thank you. Thank you. My band is very amateur. I think that's the key word. And Lou actually reciprocated by telling me that she plays the drums, the keyboard, and the piano, and has a music studio in her house. And the only instrument she doesn't have is the bass. So I invited myself to join your band at the same time. All right, so first of all, it's such an honor to be invited to speak at this incredible symposium, especially since we're, in part celebrating the life and the career and the impact of Bill Nix. So that just adds to the honor, but it's also really great to hear from so many alumni of the department and to see how successful this department has been in producing the next generation of human capital, which always gives me a lot of optimism about where science is going to go in the future. And I'm not really a card-carrying material scientist by any stretch of the imagination. I'm more of a chemical biologist who also studies the biomedical significance of cell surface glycans. So people might think of me as a glycobiologist as well. And so I thought I would talk about some research that we've been doing in my lab over the last 10 years or so that focuses on the cell surface glycocalyx, as we call it. And that's a term that literally means a cage of sugars that coats the surface of all of our cells. And I became interested in the cell surface glycocalyx back during my training years when I learned that cell surface glycans are really important mediators of cell-cell communication. So when two cells come together and touch for the first time, first point of contact is these cell surface sugars. And as this cartoon might illustrate, they're literally like a forest that covers the surface of the cell, and they're made up of complex chemical structures that are in no way arbitrary. Serve very important biological purposes, some of which are very specific in terms of receptor-ligand interactions, but others are more like from the material science point of view. And I'm going to tell you two vignettes about cancer cell surface glycocalyces, the first of which is a biochemical story, and the second of which is more of a materials story. So all of this starts with the observation that dates back more than half a century, that among the molecular changes that a person can observe between healthy cells and cancer cells are some stereotypical changes in the patterns of cell surface glycans. So the healthy glycocalyx is different from the cancer glycocalyx, and this has been known for a long time. But until recently, we did not have a good idea as to why these changes occur, what they might contribute to disease progression in cancer, and then ultimately how we might leverage this knowledge to develop new kinds of cancer therapies. And that's something that my lab is very interested in. So the two cancer phenotypes that I'll talk about today are, first, the observation that cancer cells often undergo an increase in cell surface density, or cell surface expression, as we would call it, of glycans that terminate with a sugar called sialic acid. And the pink structure is for any chemists who really want to know what these sugars look like. But you can kind of look at a high level at these pictures, and I think this reflects what we understand from our analytical work, which is that healthy cells have glycans, they're these branched polymer structures, with sialic acids on them. We call them sialoglycans. And all healthy cells will have some arrangement of these sialoglycans, and I like to analogize that arrangement to like a well-manicured garden in your backyard. But the observation is that cancer cells often overproduce these sialoglycans so that the well-manicured garden turns into like a tropical jungle, just a big mess with a lot more sialic acid sugars in different geometrical arrangements. And one of the geometrical arrangements that these sialic acids can be found on are a class of glycoproteins called mucins. And the mucins are where I start to think more like a material scientist. I'm going to talk about them later in the talk, but they have physical properties that are quite distinct compared to other biological molecules and compared to anything else on the surface of a cell. And we think it's their physical polymer-like properties that contribute to cancer progression. And I'll talk about that later. But both of these phenotypes are quite prevalent, have been observed over many decades, and we've been using chemical tools in my lab to try to understand what these things are all about. So the first story focuses on sialic acid. And what we discovered, now dating back to around the time I moved from Berkeley to Stanford, so it's about 10 years ago now, is that those sialic acids are playing an important role in the relationship between the cancer cell and cells of our immune system. So probably people here know that cancer immune therapy is one of the most important breakthroughs in oncology in our generation. And Stanford happens to be a real big player in the development of new immune therapy types, both molecules that activate the immune system against cancer, as well as living cells that can be introduced into patients that hone in on cancer cells and kill them. What all of these immune therapies leverage is the fact that our immune cells are equipped to recognize when cells of our body have become damaged, which is the case for cancer cells. And the immune cells, which in this graphic are the green cells, They patrol the body, and they sample all of our cells one at a time and look for evidence of damage. And if they sense that damage, they will launch an attack and kill that cell. So every minute of every day, your immune cells are protecting you from cancer. And most of the time, this works out quite well for us, right? Because most of us spend most of our lives cancer-free. But once in a while, we're not so lucky, and a cancer cell can kind of take up residence and survive and thrive and proliferate and metastasize. And in those settings, usually there's been a breakdown of the ability of our immune cells to recognize the cancer cell and to kill the cancer cell. So immunologists have been studying the molecular basis of all of this for several decades now. And one of the big breakthroughs of the early 2000s was understanding how immune cells recognize a cancer cell and make the decision as to whether to kill it or not. And this is a big oversimplification, and any immunologist in the audience would groan and shudder and cringe at this, but this is how a chemist likes to think about things. Think of a synapse between your immune cell and a target cell. And the immune cell has dozens of receptors that are looking to engage with dozens of ligands on that target cell. Some of those receptors are what we call activating. What that means is when they are engaged at the synapse, they signal to the immune cell in a positive way that something is wrong. And if enough of that activating signaling gets recognized by the immune cell, it will react and literally drop a bomb and kill that target cell. And the ligands that are on the cancer cell that are engaging with the activating receptors are molecules that are signatures of poor health, or damage signatures, as we call them. And they literally come from damaged DNA. So all cancers begin with damage to the chromosomes, to the DNA, and some of the DNA is transcribed into RNA and translated into proteins, and those proteins that come from mutated DNA can literally be displayed on the surface of a cancer cell. It's a way of the cancer cell telling the immune system, something's wrong with me, get rid of me now, before things get any worse. Now, in parallel, immune cells have receptors that are inhibitory. They're pretty much the opposite. If they engage molecules on the surface of a target cell, they will deliver an inhibitory signal to the immune cell that turns it off. They literally will quench any signals that come from the activating receptors. And those receptors are looking for ligands on a target that are kind of healthy signatures. And why would an immune cell do this? Well, the job of an immune cell is pretty difficult because it has to determine which of your own cells are healthy and which are diseased. Kill the healthy ones and not kill the diseased ones and not the healthy ones. And if the immune cell accidentally makes a mistake and kills a healthy cell, that leads to an autoimmune disease. So these inhibitory receptors protect you against unwanted immune reactivity. And ultimately, the immune cell has to integrate the signals from both activating and inhibitory receptors and try to make a good decision. So the big discovery in oncology is that those inhibitory receptors are leveraged by cancer cells. A cancer cell, or a cancer in general, can evolve to present those healthy signals as a way to trick the immune system into leaving it alone. And a cancer cell that's able to do that is one that lives another day, proliferates, and thrives. Likewise, if you can block immune cell inhibitory receptors from interacting with their ligands, which people have now done with drugs, you can literally potentiate the activity of an immune cell and give it a better chance of recognizing the bad guys and killing them. And that's exactly what the so-called T-cell checkpoint inhibitors do, or the checkpoint blockers. They're typically monoclonal antibodies that bind either the inhibitory receptor or its ligand, interrupt the inhibitory signal, and allow the immune cell to react to a positive or activating signal. And the two T-cell checkpoint receptors that are kind of household names in this business are PD-1 and CTLA-4. And the folks who discovered those receptors and their biology received the Nobel Prize in Medicine or Physiology back in 2018. So why were people so excited to the point where these folks were recognized with the Nobel Prize? It's because certain types of cancers that were previously 100% lethal suddenly became treatable, and for a minority of patients, even curable. So for example, in the world of immune oncology, This chart is kind of like the Mona Lisa. Like everybody recognizes this from a mile away. It's kind of a famous so-called Kaplan-Meier curve, which basically was a phase 3 clinical trial readout for patients with metastatic melanoma. So this is skin cancer that's metastasized around the body. And these patients were treated either with one or the other of blocking antibodies against the checkpoint receptors or a combination of the two. And what you can see here is that over time, as patients were treated with these immune therapies, some of the patients did not survive, but eventually there was a plateau where after several years, anywhere between 30 and 50% of the patients were still alive. And that was completely unheard of for metastatic melanoma. This was a 100% fatal disease before the advent of these immune therapies. So the biopharmaceutical industry made an enormous investment and doubled down and tripled down and quadrupled down on this biology to the point where nowadays you have your choice of antibodies that block these receptors or their ligands from pretty much every major pharmaceutical company. And the big 800-pound gorilla here is the Merck drug, Keytruda, which is sort of the top-selling Merck drug of all time. Now, on the one hand, these medicines were miraculous for certain patients, but on the other hand, they were not miraculous for most patients. Even in the setting of melanoma, which is the cancer type for which these are most effective, maybe half or slightly under that of patients actually enjoy this benefit. But the majority of patients don't respond to these medicines in such a dramatic way. And for other types of cancer, the response rates are even lower. So while, if you're a patient with one of these diagnoses, you have a shot here, most patients are not going to win that gamble. So the big question over the last decade is, why don't these drugs work spectacularly for more patients? What are we missing? Do we have a full understanding of the molecular mechanisms that allow cancer cells to manipulate your immune cells? And are there other targets that we might go after so that more patients can benefit from immune therapies? And this is something we've been thinking about in my lab. Which brings me back to that sialic acid sugar, which is so dramatically overexpressed in the tropical jungle of the cancer cell versus the well-manicured garden of the healthy cell. It turns out we have a family of sialic acid binding receptors on immune cells that modulate immune cell function. These were discovered courtesy of the Human Genome Project back in the early 2000s. They are now known as the sialic acid binding immunoglobulin-like lectin family, which we abbreviate the SIGLEC family. And this graphic shows their domain architecture, where the yellow line is the membrane of an immune cell, and what's above the yellow line is the extracellular part of these proteins, and what's underneath the yellow line is the intracellular or cytosolic part. On the outside, all of these members of the SIGLEC family, and we call them SIGLEC 1, 2, 3, 4, 5, et cetera, they have that crescent moon shape which binds the sialic acid, and they all share that common capability, that they can bind glycans that terminate with sialic acid. What was so intriguing to us was what was below the yellow line, the cytosolic signaling domains of these receptors. Many members of the family have these purple blocks and red blocks with these acronyms, ITIM and ITSM. Those are jargon that immunologists use to describe domains that allow inhibitory signaling. And if on a cartoon like this, you also showed one of those T-cell checkpoint receptors, the one that's called PD-1, it's the target of Merck's drug Keytruda. If you look what's inside the cell, PD-1 has the same domains as several members of the SIGLEC family. So biochemically, these receptors, we thought, could behave very similarly, and maybe just is able to signal to the T cell that it resides on, go to sleep, leave the cell alone, everything is fine. Likewise, maybe some of these SIGLEC receptors might also be telling immune cells to go to sleep, and not just the T cell. Because the SIGLEC receptor family, they're found on every different flavor of immune cells, and there's lots of different flavors.
So it's a bit like the military-industrial complex, where you have the Army, the Navy, the Marines, and the Coast Guard, and so on. And all of these immune cells can contribute to anti-cancer immunity. And so we thought maybe the reason the T-cell checkpoint receptor blockers are not working for everybody is that they're hitting a subset of patients for which PD-1 is an important node of immune suppression, and only on the T cell. But maybe for the patients that don't respond, maybe the Siglecs are contributing, and maybe across a much broader set of immune cells. And so we started drawing cartoons like this one, where we said just as a T cell can use PD-1 to engage with its ligand on a cancer cell, which allows the cancer cell to hypnotize and put that cell to sleep, maybe likewise, those sialylated glycans on the cancer cell are engaging the Siglecs and putting immune cells to sleep that way. And that might explain, finally, why it is that so many cancers have been found to be hyper-sialylated. That could be a phenotype that gives them an advantage through natural selection. So we went about testing this hypothesis experimentally, and I won't go through the details because all that work is published, but to make a long story short, we realized that these sialoglycans and the Siglec receptors they engage are a major axis of immune suppression in the context of cancer, and we think that that might be the area of biology where you could design a next-generation immune therapy. So we came up with an idea as to how to target that biology. And because there's so many members of the Siglec family, there's 14 of them in human, it would be really hard just to block those receptors. There's just too many of them. There's only one PD-1, so you can make a drug like Keytruda and you've got the biology covered. But with the Siglecs, it's just not that simple. The one thing that all those Siglecs share in common is they want to bind a sialic acid. So we had a different idea, which was to develop a medicine that might function like, as shown here, a lawnmower. Imagine parking a lawnmower on the surface of the cancer cell and literally mowing that lawn and just stripping off the sialic acids and sending them off, into the stratosphere and leaving the cell naked and exposed and unable to engage the Siglecs. So our idea for a lawnmower basically took the form of an antibody-enzyme fusion. We took antibodies that target cancer cell surface antigens, and we fused them to enzymes called sialidases. And these are enzymes that are known in the natural world that catalyze the cleavage of that sialic acid sugar off of the branch that is basically displaying it on the surface of a cell. And so the way that these molecules work is they park on the cancer cell, the enzyme just starts cutting and cutting and cutting, and you can literally strip a cell of its sialic acids, which then allows immune cells to be much more reactive against it. Here's an example of some preclinical data that we acquired in collaboration with Heinz Laubli, who's a physician scientist at University Hospital in Basel. And his lab had set up a model for breast cancer in which breast cancer cells are engineered to express a human cancer antigen called HER2. It's a protein. And then those mouse breast cancer cells are injected into the mammary fat pad. So they're grown in the mouse breast tissue. And this particular type of breast cancer is known to be resistant to an antibody called trastuzumab, which is an FDA-approved antibody against HER2. And it's used to treat breast cancer patients, but it doesn't work in this mouse model. And what we did is we fused to that anti-HER2 antibody a sialidase to take off the sialic acids and then see if the mouse's own immune system could help eradicate the tumor. And you can see here that when mice are inoculated with these tumors, they'll start to grow, and what's being measured on the y-axis is the volume of the tumors as they grow. And you can inject those animals with just a saline solution, that's PBS, or with the naked FDA-approved antibody, trastuzumab, and there's no difference in the way in which the tumors grow. But if you treat them with our fusion of trastuzumab with a sialidase, which we call T-sia on this graph, now those tumors have a much harder time growing, and if you isolate the little nodules, you'll see that it's mostly made up of immune cells and not cancer cells. So Lou was talking about, how Stanford's such a great environment in order to spin out companies from your basic science, and that's something that we did. And in fact, I landed here in 2015, and that same year, within a few months, we spun out a company called Paleon Pharmaceuticals, which is in Boston, Massachusetts. And the scientists at Paleon have now kind of engineered the structures of these antibody enzyme fusions so that they're more developable as human medicines. So for example, whereas we had made some prototypes with a bacterial sialidase fused to the human antibody, the scientists at Paleon kind of changed up the architecture so that they would have a human sialidase, which is much better for a human drug, fused in a different way so that the molecule overall has a mass that's more similar to a natural antibody and not to this much larger molecule that we had made. And that molecule there is now going into humans in a phase 1 clinical trial in the second half of this year. So we're all crossing our fingers that we're right about the biology and might be able to bring a new type of therapy to cancer patients. Now, in parallel, we were thinking about this mucin phenotype, the fact that so many cancers overexpress a certain type of glycoprotein with very unusual structural and physical properties. So let's talk a little bit more about mucins. I first became interested in these mucins actually back when I was running the Molecular Foundry. And at the Molecular Foundry, we had an entire floor of the institute that was focused on the biology nanoscience interface, the so-called bio facility. And in that facility, I had a couple of postdocs that were working on lubricious coatings of materials to make them more biocompatible. And you can think of mucins in nature as being like the natural lubricators, the natural passivators of tissues and cells in the body. They prevent unwanted interactions, but they can also engage in very specific wanted or intentional interactions. And they're really quite remarkable materials. So the defining attribute of a mucin glycoprotein is basically long stretches of serine and threonine residues along the polypeptide backbone, where many of those residues are glycosylated with a certain type of glycan structure. And so the middle cartoon there is kind of the chemical structure that you would see if you kind of, sort of zeroed in on the backbone of a mucin, where you have serine and threonine residues all right next to each other, dense clusters of glycosylation. The glycosylation is so dense on a mucin that it forces the backbone into a rigid, extended conformation. And so when mucins are anchored to the plasma membrane with transmembrane domains, they tend to stand up tall and rigid. And again, back to the landscaping metaphors, you can think of the mucins as the giant redwood trees on the surface of the cell, whereas other types of glycoproteins are smaller and kind of under the canopy of the mucins. Mucins can tower 10 to 100-fold taller than your average cell surface protein. Now, many years ago, back at Berkeley, we were making mucin glycoproteins and studying their physical properties, and so we know that it's the density of glycosylation that gives them the stiffness that they enjoy. So for example, we were making mucin glycopolypeptides with different densities of glycosylation and analyzing them by atomic force microscopy. And you can see here from these pictures that when mucins are 100% glycosylated, every single residue has a sugar on a serine or a threonine. They're so rigid that when you put them down on a slide and take an AFM picture, they look like toothpicks. And if we look at their persistence lengths, they're more rigid than double-stranded DNA. So they're pretty stiff. And by contrast, when you start to dilute the glycosylation on the backbone, then they become a little bit more flexible and a little bit more curly. But in a biological context, when they're heavily glycosylated as they normally are, and therefore very rigid and stiff, they tend to form a barrier on the cells that they're attached to. And the penetrability of that barrier kind of depends on the density of their expression. Now, we knew that they were overexpressed in cancers. That literature went back for many decades. And we were trying to understand, what is it about having density of cell surface mucins that might somehow promote disease in cancer growth and metastasis and poor prognosis in patients? And we got a hint as to what might be going on when we read a paper published by Valerie Weaver's lab at UCSF. She is a cancer cell biologist who studies how the biophysical properties of the tumor microenvironment affect the human disease. So her lab had a long history of, for example, measuring the stiffness of the extracellular matrix, the Young's modulus, and correlating that with cellular properties in the setting of cancer. And she had a former postdoc named Matt Patzek, who is now on the faculty at Cornell, who basically crafted a computational model to try to predict what might be the consequence of a stiff mucinous glycocalyx on the ability of a cancer cell to interact with extracellular matrix components in its environment. And to make another kind of long story short, he made this kind of paradoxical prediction. Now, on the one hand, when you look at cartoons of mucins and think about dense coatings of mucins on a cancer cell, you might think that having a dense mucinous coating would interfere with the ability of that cancer cell to engage the extracellular matrix or other cells around it. But in contrast, what Patzik's model predicted is if you have a stiff or thick glycocalyx, rather than preventing adhesion to things in the environment, that actually might maybe slow down adhesion, but ultimately promote more biologically relevant and impactful adhesions. And the reason is that cancer cells, like all of our cells, have adhesion molecules on the surface called integrins. Integrins anchor to the extracellular matrix. When integrins form large clusters in those anchors, they signal through what are called focal adhesions. And the signaling that comes from those focal adhesions allows cells to survive, to proliferate, to migrate. These are all behaviors that contribute to cancer progression. Now, his prediction was when you stiffen or thicken the glycocalyx, you're basically forcing integrins to engage with the extracellular matrix only in regions of membrane curvature. Membranes are pretty fluid. Biological membranes have a lot of features, and they'll curve. And when they do curve, an integrin can latch onto something in the extracellular matrix because it can penetrate through that glycocalyx layer. And as soon as there is a membrane deformation, any integrin that happens to be nearby will very rapidly also engage the extracellular matrix. So the ultimate prediction is stiffening or thickening the glycocalyx promotes membrane curvature and larger focal adhesions through what he called a kinetic trap mechanism. We saw this paper published back in 2009, and we thought, this is a really interesting theoretical prediction. Can we get experimental evidence for this? And so we did. We formed a collaboration with Valerie and with Matt, and over the next 5 years or so, we published some papers, but basically, the upshot is that the thicker and the stiffer the glycocalyx becomes, which is the consequence of mucin overexpression, the larger these focal adhesion plaques become, the stronger the signaling is, and that is pro-oncogenic to a cancer cell. It enhances their survival, their proliferative ability, and their ability to take up residence in a metastatic niche. And all this is published if you really care about the details. Furthermore, we did experiments showing that if we intentionally engineer cancer cells, either with a thin, low mucin glycocalyx or a thick, high mucin glycocalyx, you can dramatically impact metastasis and disease progression in an animal model. So this is a model where we took these engineered cells, inject them into a mouse, and let them metastasize and grow nodules in the lungs. Mice that were injected with cancer cells with low mucin, those are the lungs on the left-hand side, they have very few metastatic foci, whereas lungs from mice inoculated with very mucinous cancers are riddled with tumors. So the bottom line is that that material coating of the cancer cell leads to a biological consequence that promotes cancer. And if this is true, that going from a thin, healthy glycocalyx to a stiff, mucinous glycocalyx leads to all of these unwanted outcomes, maybe you could reverse that in a therapeutic context with a drug that takes those mucins off. So how do you do that? Well, just as we made a lawnmower for the sialic acids, we thought, I think we need a chainsaw now, because we need to cut down a forest of giant redwood trees. So is there a therapeutic molecule that could do this to a cancer cell? And again, we looked to enzymes from the natural world. It turns out that, first of all, your gut is a very mucinous environment. Secreted mucins are the major component of mucus, hence the name. So any organ or tissue in your body that has a mucus coating, you got a lot of mucins there. And this is true in your gut. And the microbes that have to inhabit this very mucinous environment, they produce proteases called mucinases. These are literally chainsaws that are very selective for cutting the backbone of mucins. Your gut microbes need these mucinases because they have to navigate through this very viscous material. So it's helpful for them to be able to chop it up into smaller pieces. Also, if they can chop up the mucins into small pieces, they can use them as a food source. So we cloned a bunch of these mucin-specific proteases from various gut microbes. We characterized them. This was the brilliant work of a former postdoc, Stacy Malacher, who's now on the faculty at Yale. She's a mass spectrometrist, and she was able to map where exactly a variety of different mucin proteases were cutting, and to identify mucin proteases that would also cut cancer-associated mucins. And that odyssey led us to identify a particular mucinase from E. coli, which is called STCE. That's the name of the gene that encodes the protein. We just call it sticky for short. And sticky is a remarkable enzyme. It has 3 domains. The catalytic domain is a metalloprotease domain. It's the gray part in this cartoon. And then there's 2 other domains, the so-called C domain and INS domain. These are like little hands that grab onto cell surfaces. So this enzyme can literally latch on with its 2 hands, and then that metalloprotease is like a mouth, and it just kind of munches on the mucins on the surface of a cell. And it will do this to cancer-associated mucins. So we thought maybe we can engineer this enzyme so it will do all of its munching on cancer cells selectively without taking the mucins off of healthy cells. So this was an engineering challenge, and we thought the first step would be to detune the enzyme, literally disable it, so it can't just go around kind of willy-nilly, indiscriminately cutting mucins off of any old cell. And the way we disabled it was we removed the INS domain and the C domain, the 2 hands, so it can't just latch onto a cell indiscriminately. And then we made the mouth a little less aggressive by putting a point mutation in the active site, which diminished the binding affinity to its mucin substrates. It didn't kill it altogether, it just diminished the binding affinity. And then the idea was to take that disabled enzyme, that detuned enzyme, which is now in the middle cartoon, and then make it more active only on the target cells of interest by fusing it to a tumor targeting protein. And in this case, we used a nanobody, which is like a little fragment of an antibody against that same breast cancer antigen HER2 that we had used as a proof of concept for the sialidases. Okay, so again, the idea here is that the disabled enzyme on its own is not good enough to rip mucins off of any old cell. But when it's got that nanobody on it, now you can anchor it on the surface of a cancer cell, and then the effective molarity of the enzyme with the surrounding substrates is high enough to overcome the limitations we imposed on it through mutagenesis. So this is how we get the targeting that we want. And this works beautifully. So here are some data in which we took some cells that express a cancer mucin called CD43, and we treated these cells with different reagents. And the graph on the left is the cell without the antigen HER2, and the graph on the right is the same type of cell, but now with the antigen HER2. And the blue line, it shows the removal of the mucin when you treat these cells with the wild-type enzyme. So at picomolar concentrations, the wild-type sticky just cuts the forest off of these cells. But after we detuned it by taking off those domains and making the active site point mutant, that's now the gray catalytic domain. It's much less active against these cells. It's about 4 orders of magnitude different in its activity. And when we put the nanobody on it, the activity doesn't change because these cells on the left do not express HER2. There's nothing for the nanobody to bind to. By contrast, you look over to the right, now the cells do have that cancer antigen. And now, when you treat them with that detuned enzyme with the nanobody, you get just as much activity as with the wild-type enzyme. So you rescue the activity only on the target cells, whereas the detuned enzyme without the targeting element is still essentially inactive, at least at relevant concentrations. And most importantly, when we teamed up with Valerie Weaver's group, we showed that these targeted detuned mucinases can reduce metastasis and reduce tumor growth in animal models. So here's an example of a model where we took a mucin-positive, HER2-positive breast cancer cell line and grafted it into a mouse. And then at different time points, we treated these animals with the targeted mucinase. And what we showed is that the volume of the tumors are reduced, and the extent of metastasis is also reduced. So we think there could be a therapeutic play here. In order to get something that's more developable as a human therapeutic, we think we will need a human protease. Not a mucinase from bacteria, like sticky, but something that's more human-like. And so right now, that's pretty much the focus of the subgroup in my lab that works on this, is trying to find and engineer a human protease that can behave like this bacterial protease. So with that, hopefully I have given you a flavor of the kind of work we do in developing new therapeutic modalities that target the cancer glycocalyx, either to reverse some biochemistry that leads to immune suppression, or to take off really stiff, rigid polymers that are causing havoc in the setting of cancer. I started, here's a take-home message, by telling you that tumor sialoglycans are overexpressed, and they engage these Siglec receptors to drive immune suppression. And if we can target a sialidase to cancer cells and take off these sialic acids, that can be therapeutically beneficial. And then in the second part, we talked about how mucin overexpression causes a stiffening and a thickening of the glycocalyx, which has consequences in the size and the activity of focal adhesions and cell biology. And by repurposing a mucin protease, we can cut those glycoproteins off the cell surface and basically deprive the cancer cells of some of these capabilities. The first story has led to a translational story, a new company, and hopefully clinical success. We should be so lucky. And the second story is still kind of in the early preclinical development phase, but if anyone here thinks that there's a there to spin out a company, I'm all ears for that. Okay. So with that, I owe my coworkers a deep debt of gratitude. This was the work of many students and postdocs over more than a decade now, and I didn't mention all their names in passing. There's too many contributors, not enough time. I do want to particularly shout out the fact that none of this would be possible without what I have enjoyed over, by now, a 30-year career, which is continuous stable funding from the federal government. So this work, thank you, you're right. This is something that most of us will share in common here, which is that we enjoyed the support, typically and historically bipartisan, of the federal government to invest in the early stage research that we perform in our academic labs. And in the context of receiving money from the National Institutes of Health, for example, I've been able to train now over 200 coworkers that basically are contributing to our economy, and to spin out 14 biotech companies, which created hundreds of jobs. And so one hopes that these messages make it to the ears that need to hear them, that continued support for our research is absolutely vital to our economy. So if you take home nothing but that, hopefully that has some value. So thank you very much for the invitation. I appreciate it.
Carolyn, very exciting. I want you to put on your business hat and think about IP for a moment. Back in 1981, Herb Boyer up at UC San Francisco and Stanford people put together the recombinant DNA patent, and that's sprung off $300–400 million for Stanford over the years, just licensing that patent. Do you see opportunities for engineering things now and in the near future that might have similar repercussions on the university as well as private companies that you may be working with, maybe with Valerie Weaver or other people doing exciting work?
This is the dream of many academics, is that we make a discovery so impactful, or we create an invention that's so important that not only does it launch an entire industry, but it comes back to feed the needs of the university, which are growing. So we should all be so lucky as to have made a contribution that significant in our lifetime. The Herb Boyer patent was kind of a generational situation, but my former institution, UC Berkeley, now enjoys quite a bit of revenue from the CRISPR patents. Even though they lost several legal battles, still, the battles that they won have been pretty lucrative for them, and it's just the beginning. So I would like to think that the work that we do is going to have some impact, first and foremost, on patients. If there's financial benefits to Stanford, I'll feel even better about that. It's hard to predict right now how that's going to play out.
Yeah, I have a question. The sialoglycans that you are talking of, probably the healthy cells need them for some regular metabolic pathways as well. So how do you target them to the point that they are not destroying the ecosystem?
Yeah, this is a great question. You know, how do we ensure that we're not mowing the wrong lawn and cutting the wrong forest and doing sort of, you know, ancillary unwanted damage to the system? We do our best to target these enzymes to the cells that we think need to see them. But there's always some off-target activity. It's hard to avoid that entirely. And the side effect that we worry most about is autoimmune side effects, which are in fact the side effects of immune therapies in general. Right, so patients treated with Keytruda, or more recently with, for example, a CAR-T therapy from Stanford University, often do have autoimmune side effects that can lead to chronic conditions. So some of them develop type 1 diabetes, which is autoimmune reactivity against the pancreatic islet cells. They might develop Crohn's disease, autoimmune reactivity against cells in the gut. But you know, you can manage and live with those conditions, whereas you can't manage and live with metastatic melanoma without an immune therapy. So you know, that's the calculation people do. We hope, and I could stand here and rationalize why our approaches will maybe be less, you know, sort of mitigate some of the risks of these autoimmune side effects. But I think, you know, realistically, we should be very cautious about those kinds of side effects, and I don't think our drugs will be perfect.
Hi, Professor Bertozzi. Something I appreciated about the entrepreneurship panel was the discussion on intersecting material science with commercialization and AI. So it looks like you have the commercialization part done with Palion, but I was curious if you were thinking about machine learning and AI in your research at all, and how that can contribute to specifically your lab or the broader field in general.
Thank you for asking that. I think it's a very relevant question for all of us to think about. Are we doing the best job we can, leveraging that leading edge of AI to help in our research, whatever our research might be? And we have leveraged some machine learning capabilities. In fact, one of the 14 companies that I spun out from Stanford is a cancer diagnostics company that basically takes it's a blood test, take blood samples from patients, and we characterize the serum glycoprotein by mass spectrometry. And what comes from those experiments are massive data sets. And being able to extract useful diagnostic information from these massive data sets is very much a machine learning problem. So that's one, you know, context in which we not only have used machine learning capabilities, but we're trying to commercialize them in the form of a cancer diagnostic. Also, being able to predict the glycostructures on the surface of a cell, that's something that is not in our capability yet. Glycans in the field of glycobiology in general is a technically complicated field that doesn't directly benefit from some of the big advances in molecular biology that, for example, the Herb-Boyer patents leveraged. For example, if you want to know whether your cell has certain mutations, suppose you want to characterize cancer mutations, you do DNA sequencing. And DNA sequencing nowadays is quick and cheap. So you can do it at the single cell level on a biopsy sample from a patient overnight, pretty much. If you want to know what proteins a cancer cell is making and look for biomarkers for diagnosis, well, it's harder than sequencing DNA, but we have techniques to characterize the proteins and figure out what's coming out of the cancer cell versus the healthy cell. By contrast, the glycocalyx, or the glycome more broadly, cannot be sequenced quickly, cheaply, easily. That capability doesn't exist yet. So if there was some way that we could actually infer the composition of the glycome by doing things that we know how to do, like sequencing the genome, that could be really powerful. But how do you link the genome and the glycome when they're pretty far apart from each other in biology? Machine learning might be a way to do that. You know, maybe you could train an algorithm to learn how to predict a glycocalyx from a genome. And I think that's something I'd be very interested in thinking about. Thank you.
Well, thanks, Carolyn, for a great talk. Maybe you noticed also there are some concepts that are familiar to us. There was some surface science there, mechanical properties of membranes, nucleation of integrin, integrin domains. So at the very fundamental level, I think there are some really interesting connections. And also at the more applied level with drug delivery and materials for drug delivery and so on. And I should add that Carolyn is a big proponent of connecting our disciplines. I think there's some really exciting opportunities there. I hope we can make this happen in the near future. And now it's my great honor to introduce our very own Bill Nix, who will give our closing remarks for this year Bill Nix Symposium. Bill, please come to the podium.
Thank you, Alberto. Thank you for inviting me to be here, to talk. You know, I always talk. But thank you so much, Alberto, and also the MSc faculty for setting up this lecture. And what's great about it, it brings all of us together. That's the best thing about it. And so thank you for that. And I should thank Chris and the MSc staff for making this run so smoothly. Each time we've done this, it goes very smoothly. So thank you for those of you who organized this and put it together. And so I also want to especially thank Carolyn for a brilliant lecture. And you know, as she was talking, you know, if you keep going, I might make it to 100. I'm pretty confident of this now, having heard your lecture. So thank you so much for what you're doing, and also to Gosang and Andy for again showing us that the future of the department is very bright. You saw it in what they're doing, and that's the projection, and you saw it in the charts also that Alberto showed, that things are looking up in this time. And finally, to E and his panel of former graduates, demonstrating and showing us that there is life after academics. A lifelong academic, it's nice to know that there's something else out there. So maybe some of you, so you've heard about the future mostly all morning. It's all about the future. So I want to tell you something about the past, and so that'll be my. So some of you may know that I was elected this last year to the Royal Society of London as a foreign member, and one of the traditions is that when I will be inducted in July if I'm able to make it, but they ask you to give a very short talk on why it is that they sort of forgot already, but why is it that you were elected to the Royal Society? So I have to come up with something to tell them. So, you know, I thought it might be useful for me to give this little talk and to tell you what it is that they elected me for, and it's a way to tell you what my students mostly and I have been doing for the last several decades. I did talk about the past. So let me tell you this story. In 1638, Galileo, now I did say we were going to talk about the past, so well, that is really the past. So Galileo in that year published a book called Two New Sciences. You can find this book in the Stanford Library, and many libraries, I suppose. I've seen it. And in it, he explains and describes, he says that for the case of a bar in tension, that the maximum load that bar can sustain would be directly proportional to the cross-sectional area of the bar. That's what he said in 1638. Well, many of you know that the load divided by that area is what we call the strength, the tensile strength. So because the load is directly proportional to the area, and it's the load divided by the area that defines the strength, it means that the strength is independent of the size. It doesn't matter whether you have a small thing or a big thing, the strength doesn't change. And so we call it an intensive property. It doesn't depend on the size. Now, in the case of this idea that the strength doesn't depend on size has guided engineers for almost 400 years now. You want to support a bigger load that's bigger, twice as big in area, then you need, sorry, I said it wrong. If you want to support a bigger load by factor of 2, then you need an area by a factor of 2. And that's how we design the world. The whole world's been designed that way for nearly 400 years. So in the language of mechanics, it means that there's no length scale. It doesn't matter whether it's big or small, strength is the same. In fact, if you look up in Wikipedia now, today, if you look it up right now, get on your phones, look up Wikipedia, strength of materials, and it says it's intensive. It does not depend on the size, and that's what Galileo told us a long time ago, and it applies to structures from millimeters to meters in size. So that's a long-standing principle. But about 40 years ago, we and others found that the mechanical properties of metals, particularly metals, in sub-micrometer dimensions no longer follow that rule. That Galileo's rule starts to fail at that small scale. And why were we interested in this? Well, integrated circuits are made out of ever smaller things, as you all know, and it was known starting to be known in the early 80s that there were mechanical reliability problems that arise. So that we knew and discovered that the materials at that scale are subjected to very high stresses, and they can fail and deform, and all kinds of bad things happen. So the whole issue of reliability is what brought us to look into what the mechanical properties are on that small scale, much smaller scale than we had ever thought about before. So the next question then, well, okay, we need to look into this and learn about it and understand it so we can control it. So the next question is, how can you study the mechanical properties? I mean the basic mechanical properties at such small scales. We regarded microns as small scales in those cases, compared to the big bars that we used to pull in tension and fail and all that. So how do you do that? Well, we discovered, or we knew about, nano indentation, which had just recently been developed by mostly John Pethica, and who was a student of David Tabor, both a pioneer in indentation hardness measurements. So we thought that would be a good thing to follow. And so we picked on nano indentation as a way to probe and understand mechanical properties at this ever smaller scale, which was needed for reliability. Well, many of you know, maybe most of you know, that nano indentation involves pushing a very sharp pointed indenter into the surface of a solid, say a metal. And then you measure the forces and the corresponding displacements as that indentation process goes on. And it's the hardness, which is the basic mechanical property, is simply the imposed force divided by the projected area of the contact. And we developed a method. These contacts are very, very small. You could see them in electron microscopes, but it wouldn't be easy to see these, certainly not with the naked eye, and even not with an optical microscope. So we developed a way to determine what that projected area is simply by from the force and displacement alone wwithout ever seeing the indentation. That was a development in the 80s. So now Galileo's rule, coming back to Galileo, it predicted that the hardness, which is again an intensive mechanical property, shouldn't depend on the size. It shouldn't depend on how much volume you've probed. Small, big, should be the same. But what we found was that it's not the same. What we discovered was that as you make indentations smaller and smaller and smaller and smaller, probing smaller and smaller volumes, the hardness, the mechanical property, strength, rises. And it can rise by a pretty significant factor, maybe a factor of 3 in strength. Now you say, wow, a factor of 3, that's peanuts, who cares? No, in mechanical properties, that's a big deal. If you change mechanical properties, strength, for example, by a factor of 3, that's a huge, huge factor. So it's something that had to be taken account of when these small volumes are probed. Now, having discovered that effect, and we and others discovered the effect, we immediately started thinking about, well, how could we explain this? And it didn't take long for us to figure out that the fundamental answer to this question of what's going on was really set forth almost 90 years ago by G.I. Taylor and Egon Orwan, who discovered or postulated the existence of dislocations. Most of you probably have studied line defects in crystals. As an aside, I've been a student of dislocation theory since the 50s when I read books by Alan Cottrell. Another aside, I remember there was a book, Dislocations in Plastic Flow in Crystals. Some of you may know that old book. And one appeared in the bookstore. And two of us, another graduate student and I, saw that book. And we both wanted it. And I almost came to blows getting that. I got it. I still have it. Dislocation. So I've been a student of dislocation theory since the 1950s. Now, coming back to indentation, if you make a very small indentation into a metal crystal, a pyramidal, a sharp-pointed diamond pyramidal indentation, it turns out that as you push that in, you create what are called geometrically necessary dislocations. You change the shape of the crystal, and that must mean that you're creating extra dislocations in that small volume. We call them geometrically necessary dislocations. And a very simple argument says that the density of these dislocations increases as you go to smaller and smaller volumes. The number is smaller when you make a smaller volume, but the density, the number length per unit volume, increases dramatically as you go to smaller. And a simple geometric argument shows that. And then if you use another expression that G.I. Taylor created in the early 30s, if you take account of what the effect of that higher density of line defects as you go to smaller and smaller volumes, it's consistent with the indentation size effect. That's why things get stronger as you make smaller and smaller volumes, as you deform smaller and smaller volumes. And then we continued on that through collaborations with Huazhen Gao, and some of you know, and Yonggang Wang, and then later with John Hutchinson at Harvard, we realized that when you make these small indentations, you're creating gradients of plastic strain. That's fundamentally what happens. You take a crystal and you deform it in one place and not the other, then there are gradients in plastic strain that lead to this indentation size effect. And so then we realized, well, there are other situations where you have gradients of strength, bending and torsion and all kinds of things like that, if done on a small scale, would produce the same size effect. And that led, in fact, in mechanics, that led to an approach to mechanics of plasticity called mechanism-based strain gradient plasticity, where a length scale appeared in plasticity for the first time. Before, everything was intensive and size independent. Now it becomes size dependent. So that was the story on indentation and indentation size effect. The deviation from Galileo. But then we wondered, well, what if we were to, so that's a smaller is stronger effect. You saw that in the outline here. Make things smaller, they get stronger. So we then wondered, since the indentation size effect relates to gradients of plastic strain, we wondered, well, what if you took a small piece of material and deformed it homogeneously in some way? So we used the focused ion beam machining technique to create right circular cylinders of little test samples, tiny, tiny test samples that you could then deform in compression, and so there would be no obvious gradients of strain. So, well, what if you tried to deform things on a small scale but without gradients? Well, what we discovered again was a very large, we again use the nano indenter, but now with a flat-ended punch where you just compress the little right circular cylinder. And what we found again was a very large size effect. In this case, in one case, a factor of 10 or 20 in strength. Again, that's a huge effect when in terms of mechanical things. So then of course we immediately set out to, well, what's causing that? There's no gradient of strain, but plasticity still involves dislocations, line defects that are moving around, and Orawan, he explained in the late 40s that when a dislocation moves, it bends into a curve, and the stress needed to drive that dislocation depends on the curvature. It nominally depends on the length of the piece of dislocation that's moving. And so it means, in that case, the stress that would be needed to drive that dislocation, that bowing process, depends inversely on the length of dislocation. Well, in the case of micropillars, the dislocations are interacting one with the other, and they conspire to cause dislocations to have to bow in a certain curved way, and that bowing length scales with the size of the pillar. So you make a smaller and smaller pillar, you force dislocations to bend to a much smaller radius of curvature, and that means then that the stress required for plasticity or the strength then varies inversely with the size of the pillar. So again, this can be explained using my favorite subject, dislocation theory. Okay, so that's also consistent with experiment. Now, these things that I've told you about, the concepts and the methods and the way to probe these things, it is now widely used in technology where metals in the form, materials, but mainly metals, in the form of thin films and small-scale structure are used. And I just put on something else here. Hearing Yi's panel made me think, well, I should think a little bit about applications of this. Well, in the first place, we're making things at that small scale, and to know what you're doing, you need to know what the strengths are at that, because reliability is often a problem. So just because we make things on a small scale means then that's the kind of mechanical testing and understanding that you need to follow what's going on. But that's okay for nanostructured materials. But what about bulk materials? Is this thing useful at all in any way? Well, it actually is, because what we've learned that if you make bulk materials, but if you make them in a nanostructured way, so they're individual ligaments, like a foam that makes up the bulk material, the properties are controlled by the dimensions of the individual ligaments, not by the whole solid. So you can take advantage of these huge strength effects by making nano-architected materials where the individual ligaments are much stronger than they would be were they in a bulk solid. So there are applications and there are people making those, and the properties that one can extract in that way are really impressive. So I've told this story then about smaller is stronger, and I should note that the people that I've cited, except for Galileo, are all fellows, were all fellows or foreign members of the Royal Society. Galileo lived he lived before the Royal Society was created in 1662. He had died by then, so too bad for Galileo. And it's appropriate then, having made that remark, it's appropriate for me to end this talk with a quote that some of you have heard. It's quoting a line that was attributed to Isaac Newton. Apparently it's legitimate. And Isaac Newton said, quote, "If I have seen further, it is by standing on the shoulders of giants." And it's a quote in a letter that he sent to Robert Hooke in February 5th. Today's February 18. Okay, February 15, 1676. And they, by the way, were both members, full fellows of the Royal Society. So thank you for hearing my little story. And I want to thank all of you, and especially my students, for coming here today, and also my daughter Cynthia for making sure I got here on time. And if I could just make one other little request or remark, if it were possible for my students to gather here, maybe in front, and we take a picture, and we can interpret, quote, my students broadly, however you wish. Maybe not everybody, but please, my students, please join me down here, and we'll take a photograph. So thank you.
Well, while Bill's students gather, just want to remind you lunch is served, but there's going to be also posters on the other side of the hall. Please go see the posters. Our students would love to talk to our alums. And again, I want to thank all the speakers, panelists, the staff, but most importantly, you heard what's great about today is that we're all together and we can reconnect. And we really have to thank Bill for that. We're all here because of Bill. So thank you, Bill. And then Bill's students, come on further.